Okay.
I have it already presented.
Hello? Thanks.
Okay. And we need to ask him to...
Yeah,
Parce qu'en fait, on ne peut pas nous-mêmes mettre
Ok.
on ou off.
Est-ce que vous voulez que je dise quelque chose en particulier au début là?
We want him to say something in particular at the very beginning.
Maybe the two teams are new. Like the,
I thought
Oh no, you can say that. All right. Hello, everyone. We're going to get started, so please take a seat. I hope you're all excited for this. Come again? 2 minutes. Okay, I'll still say everything. Thanks. So I hope you're all excited for this grand finals. We have some great teams today. I want to tell you a few technical things before we all start. So the whole event is being live streamed on YouTube. I put the link, okay, on the main channel on the Discord. I pinned it, okay? Please send it to your friends, your family, okay? Write some stuff in the chat. We're gonna have some nice, fun and jokes in there. And it's important that all the people who came here in front to talk or have some presence on the stage have signed the consent form, okay? If you haven't signed it, we have a few more here, okay? There's also gonna be a photographer who's gonna take some pictures. Please also tell him if something's not right. In terms of microphones, all the people in the audience, you all have a little microphone next to you, actually. And when you press on the green little button, it activates, you can talk. So for the jurors, you can actually use it, and even for the teams, you also have some here, okay? And if there is any technical issue, please come to us. So now I'm gonna give the mic to our two beloved jurors. Good luck to you all, and yeah, have fun.
Hello everyone. My name is Joachim, and this is Jean. Jeanne. And we'll be chairing tonight, and we're really looking forward to this finale between these three amazing teams. Two being in the finales for the first time ever.
Yes.
And to start with, we would like the teams to present themselves. So please stand up and present your team.
Hi, everyone. So I'm Guillaume. I'm team captain for France. I'm here with Paul, Guillaume, Robin, Martin, and Jean. What can I say? We're just really excited to be here for this finale, and we wish you all the best of luck and have fun.
So, hello, I'm Federico. I'm the team captain for Team Italy. And we have Nicola, Ludovico, Filippo, Rocco, and Marianna with us. And I just have to say that we've worked so hard for this, and we're so happy to be here. So we just want to have fun and enjoy the moment, and have a great fight.
Hi, my name is Christian. I'm the team captain of Team Germany. And with me I have Jona, Lena, Pablo, Noah, and Lisanne. For us, it's also our first time in the finale, and we're extremely excited to have made it this far. Also, I want to use this opportunity to thank all the teams we've fought so far. It's been a great tournament, and we're looking forward to another great fight.
And now we would like the juries to present yourselves. So please stand up. Anastasia, will you start?
Yes. Okay. You put on me very difficult technical challenge. Yes, I notice. Okay.
Hi everyone, I'm Anastasia, I'm IPT president and I'm gonna be a juror on this fight. I used to participate in IPT from 2011. My background is in optical communication and currently I'm an academic editor. Thanks and good luck everyone.
Christoph?
Hello everyone, my name is Krzysztof Turzyński. I'm a professor of physics at the Faculty of Physics, University of Warsaw, and vice dean for student affairs there. My background is in theoretical particle physics and cosmology. I was first involved with the International Physicists Tournament in 2016, and I got hooked since there. So I think that getting to know the IPT was one of the most important professional lessons of my life, and I'm trying to make my faculty run a little bit like the IPT, and this is a great source of inspiration. So, as to how I judge, I put a strong emphasis on communication on stage, so please remember about that, because this is what makes all the fights great. I wish you luck.
Okay, hi everyone. My name is Omar. I'm professor in the Faculty of Science and Exact Science in the University of Universidad del Valle in Colombia. I'm the team leader of Colombia. I'm very excited to be here. It's my first time, so I have some sense of excitation, by also a hesitation of being here. So good luck, have fun, and I hope you enjoyed your fights.
Hello everyone. I'm Aurelio. I'm from Spain. I'm team leader of Spain. My background is I work on nanomagnetism at the University of Oviedo, and I am really enjoying this. It is more or less what I said yesterday. It is my first time as Omar's, and it has been so nice to see how you fight, how you connect each other, how you work all together, how you push all for the same thing, and how you are having so fun with physics. So the only thing that I can say today is keep going with this direction, and do not never forget what you are doing here and why you love physics. So a lot of fun for everybody.
I'm Jean-Philippe Ansermet. I've been involved with IPT since 2014, so it's my 10th year. I'm a physics professor at EPFL, Lausanne, Switzerland. My research is in spintronics, various aspects of spintronics, and I wrote 2 textbooks, one in mechanics and one in thermodynamics. I wish you all much luck and a lot of fun.
Hi everyone, my name is Nino Kovacic and I'm a PhD student in the University of Zagreb. This is my first time at the IPT, and I gotta say, you all are absolutely amazing. Like, the energy and the passion for physics, like this is the only place where I've seen this much, I don't know, amazing, interested young people doing great work, many of them with very limited resources. So I just want to say to all, and not only the teams who made it to the grand final, well done, like amazing, and I wish you all the best of luck and have a great fight.
Good morning, everyone. My name is Yulia Zotova. I'm working as a postdoc at the Moscow Institute of Physics and Technology with superconducting quantum systems. And my first international tournament was in 2014, and I'm still enjoying it. So let's enjoy one more physics fight today again. Thank you.
Hello, my name is Frederik Durhus. I'm a PhD student at the Technical University of Denmark, working with magnetic nanoparticles. But before that, I was a participant at the IPT in 2018 and 19, and I've also been juror for a few years. And I think it's an amazing work you all did to get so far. So no matter what, you're all winners today.
Greetings, everyone. My name is Andrikopoulos Christos. I am the IOC of Greece and also a competent with a mic. No, and also a member of the Execom. I've been also a member of the IPT for many, many years now. I've been member, leader, team captain. I've been through all your positions. I know the anxiety, I know the stress. My team hasn't made it to the finals ever, so I don't know that amount of stress, but I believe that you will give us amazing presentation. I'm so excited to see what you bring to this table today. Thank you.
Okay, great. Thank you, everyone. We shall begin, as always, with the traditional captain's fights. So for this finale, we will have 3 captain's fights. The first one will be an experimental one, and all of the team members will participate within their teams. And the second and third captain's fight will be theoretical ones, and only the team captains will participate as usual. Yes. So we will ask some of the Execom members to come on stage and help us for the first captain's fight, so the experimental one.
Yeah.
And Joachim will
yes,
put the slides on the big screen so that everybody can see.
Yes. So this fight, we will be getting what is needed for the experiments. We will give you 1.5 minutes to think about how you want to do it, and then the experiment begins after that. And so I think I would like to maybe for the thinking part, you can stay at your tables, but then we will split you off in 3 separate experiments right next to your tables. Okay? Yes. Shall we go on and show the what it's about? Are you ready? Okay. So the captain's fight, you will have 1.5 minutes to discuss. And the task is to do something as fast as possible. So we will each be taking a stopwatch, and that's why we have all these members. They will each be taking time of each of your groups respectively. And so the task is you are given a large bottle of water, and you have to empty it as fast as possible. Yes, let's.
And you only have 1 try per team.
Yeah,
okay?
1 try.
Yeah.
What? Starts on the yeah, the bottle starts on the table. What?
Okay, so 1.5 minutes starting now. Okay, the timing begins as soon as they grab the bottle.
Yes.
Okay. And this is when you. Seconds left. Our mics are not functioning.
Yeah. Okay, so good.
And they should all do it like at the same time.
Yes.
Okay.
Yeah.
So who is like we should be like 2 people per team or something like this?
Yes, we need to split the Execom up. You 2 are taking time here?
Yeah.
And you 2 here, and then the 2 of you
10
there.
seconds left.
Wait. Okay. So
Wait. Can they take the bucket off the floor?
No.
Okay, the bucket.
Yeah.
Time's out, guys and girls. Okay, so that nobody cheats or copies the other team, all the teams will have to compete the tasks simultaneously, and 2 or 3 execom members will be during each of the teams. So as soon as we say, please listen to me, everybody, yes? As soon as we say start, you can take the bottle on your table, okay? And then the first bottle that is empty is going to be the winner. So is everybody ready?
Everyone at the same time.
Yes, everyone at the same time.
Okay.
You can put your bucket closer to your table if you want, because the other ones are closer. Yes? Okay, like this, it's fine, like this.
Yes.
And this.
Okay. Is all teams ready?
You can say stop.
Then
we should wait for everybody to calm down.
When I say start, you start, okay? Okay. Are you ready? 3, 2, 1, start.
Okay. That was a bit hectic, but I think we can all say without any doubt that Team Italy was first. Yes. And then we will ask the execom members to compare their chronos.
Okay. Well,
oh yeah. So Team Germany before Team France.
Okay, that was Alberto. It was yeah.
Sacrifice.
That's just the half ticket.
Okay.
Okay, so who was first between France and Germany? Germany. Is
Okay.
everybody okay with this?
Yeah. Okay.
We have
we have Italy as the winner, and then Germany as and then France. So now we move on to the theoretical captain's challenge, and so we would like to ask the captains to go on stage. No, wait.
Okay, scheiße, Fermi-Probleme. Ich hätte mich
Okay.
das sollen.
And so each of you have your pieces of paper ready and pen. Okay. And then hand me the papers when the time's up. Okay? With a circled in answer. Are you ready? Are all teams ready?
Yes.
As usual, the answer should be given with a unit.
Yes.
Otherwise, it won't be accepted.
Yes. Okay. Time starts now.
You should read the question.
Oh. What is the minimal area of a capacitor with 10 micrometers of air between the covers that could hold energy that one could theoretically get from a train going from the highest station in Switzerland to Lake Zurich. Neglect the energy losses.
You have 2 minutes and a half. One minute. Thirty seconds. Ten seconds. Okay, time's out.
Cool. Thank you, all teams, for giving it on time. And let's take a look at the answer. The solution is you can calculate the energy difference from the Zurich Sea, from Jungfraujoch, which is the highest station, to Zurich Sea, which is around 3 kilometers. And then using the capacitor law, you can calculate the amount of square meters it is. So we get an answer that is 4.6 times 10 to the 12th. And I think then this is first. Yeah. I think
you read it? I don't know.
So this means that France wins the captains.
You should say out loud.
With the answer 10 to the 14th square meters. Germany has second place with 5 to the times 10 to the 10 square meters. And Italy close by with 10 to the 10 square meters. Now we move on to the next theoretical captain's challenge. Okay. So now we.
Yeah.
What? Damn it. Okay, then we start again. So you have 1.5 minutes. So if milk was not just literally liquid gold, but with the same volume, what would the mass of gold be produced in Switzerland per year?
One and a half minutes starting now. Please, silence. Thank you. Thirty seconds left. Fifteen seconds left. 10 seconds. And time is out. Thank you.
Thank you. Okay.
Okay, let's have a look at the answer.
So the total amount of milk produced is 4 times 10 to the 9 liters. And with the gold density, you can calculate the total mass, and you get 7.4 times 10 to the 10, which means we have 2 teams that are incredibly close to the answer. I think I would actually like to take the logarithm for this, actually, just to be sure, the logarithmic distance, because, yeah, they are really close. I can, wait, can I just say the 2 answers? Team France has answered 10 to the 11 kilos. Okay. Very close answer. Where Germany has answered 6 times 10 to the 10 kilos.
And what about Italy?
And Italy has answered... It's okay?
Okay. 0.
It's not that bad.
Okay.
Yeah. It's 10 to the 20 kilos. Can anyone just quickly do the logarithm? Yeah, 6 times 10 to the 10, or 10 to the 11, which is closer to? I think that makes sense. Germany is closer, so.
Great.
Okay, so that.
Okay, so we have our final ranking. So thank you, everyone. That was a close one. So after these 3 captains' fights, Team Germany is first. So congratulations. So they arrived second, and first place, so 4 points in total. And then we have Team France. Congratulations. So Team France arrived third, first, and second, so that makes 3 points. And finally, Team Italy with 2 points.
Great
So-
job, everyone, in this captain's fight. It's really impressive to see how close you were. Everyone was really close on the first one. Okay, now it's time to do you want to choose first or second? Oh, okay. And you?
We'll choose.
Choose, yeah. Okay, then let's. What role do you want to choose first? Or
We'll
which role?
choose the second line.
The second line. So that means it's Germany. What do you want to choose?
Ja, das ist so, aber wir wollen, Denise hat gesagt, es ist wichtiger, dass wir nicht als Letzten. Pablo, bist du ready? Pablo, bist du ready? Genau jetzt.
Okay. Then we will go first.
Okay. So that means that that Italy will be moderating first.
Mhm.
Okay, so now the true fight begins, where Germany will be presenting. And do you want to tell which problem you will be presenting?
We will be presenting problem 17, thermal snail.
And in preparation time, cut my screen. Cut my screen.
Oh. Ich darf nichts sagen.
Ich darf nicht der zweite Reporter sein. Ich darf auch nicht.
Aber dann muss ich Reporter sein, dann darf ich nicht mehr auf die Bühne. Pablo, mit wem hast du?
You need to speak with the mic. Yes. 1 minute left for the preparation. Thirty seconds left.
Ein bisschen weiter zurückschieben, dass da gleich loslaufen kann. 15 Sekunden.
10 seconds. Okay, are you ready?
Yeah, okay.
Let's go.
So, hello everybody. I find it an honor to stand today here in front of you, to be in the finals and to talk about physics and present to you our solution to problem number 17, the thermal nail. So, what is the problem statement? We should build an autonomous device that only uses the temperature fluctuations during a day cycle to propel itself forward. During this, we should also minimize its length, or here restricted to a length of 10 centimeters, and maximize its speed. And we are not allowed to use any electronics at all, or we should do it purely like mechanical. So, thermal snail. You know a snail? I looked at it, and you know how a snail moves? Just like this. It contracts and expands again, and therefore propels itself forward. And that's where we came up with our intuition for our future designs. And it wasn't only one. So we had a lot of prototypes. What I'm going to tell you today is the snail movement, we did that, the thermal expansion, different concepts we tried, our vehicle, and how it performed in the end. So, thermal expansions. We define it just by the change of length over the temperature. For example, here you see a solid, and it will change its length because of the change in temperature. And alpha is our thermal expansion coefficient for this. So the first thing we tried of all the concepts were the expansion of solids. Like, that's the most natural thing you see, like bridges expand and contract, and you have to account for this. And this principle was our first concept. So we took some material with a quite high thermal expansion coefficient compared to the others, and heated it up 20 degrees and cooled it down. But the change in length was minuscule. It was only 0.136 millimeters. And you can't get enough movement from this, or at least it was not satisfying enough for us. So we also calculated the work we can obtain for this, and it was only 0.15 millijoule. So, up to the next concept, we tried bimetal, like the strips use in electric switches, for example, to trigger something when it gets heated. It is a strip of metal consisting of two different metals with different temperature expansion coefficients, and it will bend because the upper one will expand less than the lower one. So we have a strip of this here mounted solid to this plate and heat it up by 20 degrees, and we see that the change, the deformation we can measure at the end, so the very most deformation we can obtain, is quite low. So these are micrometers. We have only a change of 0.7 millimeters in total, and that was also not enough. So the work for this we also calculated, and it's in the order of 0.5 millijoules. Even though this is not that much, we thought maybe you could stack multiple of them together or in a row, or build some kinds of leverage system to get more work and especially length, movement out of this. But it really doesn't scale well, because if you stack them on top of each other, you can't harvest the same amount of force, because as you put more and more of them on top of each other, the length that it will expand and contract gets less, because you have a softer spring, softer coefficient for this kind of spring. So we thought about elongating it, but this is the same thing. You have a larger lever, so you can't obtain the same force, even though you have more displacement. And then the last thing would be like, just buy a thicker bimetal strip. But first you have to heat it up more, then it's really heavy, so the contraction needs to be strong again. And also the deformation actually gets less, because as you make it wider and wider, the differences in thermal expansion coefficients don't account for the geometry that you have here. So we have less displacement. So what's the third concept we tried? It was the expansion of gas, air, the ideal gas. So we have an air tank here that is filled with air, and it's going to be heated up, and therefore the air, according to the ideal gas law, expands. And we could move, for example, a piston here. And this is all good and fine in theory, but in reality, we have some friction, and also the temperature difference are not that great. So it's rather difficult to move a significant amount of distance here. We have this friction force at the piston, and these are the differences in pressure we would obtain from our temperature difference. So we also calculated and measured the volume change. This is the volume change, and we, from this, can only obtain a displacement at the end of the wheel of, a really small amount of millimeters, I just say. So we also calculated the work that is obtainable from this, and it's also right around the bimetal strip. It's also just about 0.5 millijoules, so not that much. What are we gonna do next? Like, these were all the things we had, but then we came up with another idea, and this was shape memory alloys. So, do I see at the time actually somewhere? Oh, sorry, okay. Shape memory alloys. Like, okay, another idea. We have shape memory alloys. I don't know if everybody knows these, but it's a metal that has some interesting properties. So it gets like made and set in the austenized phase. Here we have a spring, for example. And when you then cool it down and put force on it, it rather not plastically deforms, but has a super elastic property that will cause the crystal structure to deform in a switching way, like twinning and detwinning of these atoms. And by doing this, you can obtain a completely different shape, but without any plastic deformation. As soon as you heat it up again, it will go back to the austenized phase, and the spring, here in this example, will contract again. So you can stretch it, and then heat it up, and it will contract again. And you could easily see that this could be something useful. We could use this to do work to propel our vehicle. So we have these 3 steps here, and then we fabricated our own spring out of this nitrile metal. Nitrile is the material we used for it. This is a kind of shape memory alloy, which activation temperature you could tune between really low to really high temperatures. So you could adapt it to your outside environment of your country, for example. So we measured our string in this tensile measurement device and got these stress-strain curves. So we have the force here and the elongation here. And in this room temperature state, we elongate the spring and therefore put work into it. Then we heat the spring up, and now comes the interesting part. As we relax the spring again, the force that the spring exerts is actually higher than before. So we have this circle that goes in this positive work direction. And we did it again and again, and it worked over and over again. And the work we can obtain from this is the area between these two graphs. And this was great news for us. So we calculated the area and plotted it over the elongation, and we see this is actually the work we can obtain from this spring just by heating it and letting it relax again. But first, like you saw, we have to stretch the spring, this nitinol spring. And this is the work we need to put in to later get this trajectory where we get this red energy out. So the total would be this green curve. And this is theoretically on a realm of 125 millijoule in our experiment. So we have to set up, and we have our spring, we put work in, we have to stretch the spring first. And how do we do that? We use another steel spring to stretch our special material nitinol spring. And here we have a small problem, because as our steel spring gets smaller, the force it can exert decreases, while our nitinol spring needs more force to get stretched. So we have to do some kind of force to displacement conversion to use this efficiently. Otherwise, we would have this force to elongation graph of our steel spring to this force to elongation graph of our nitinol spring, and could only obtain this distance, which would be equivalent to only 25 microjoules, a fifth of what we could theoretically obtain with our fabricated spring. So we changed it up. This is how it should look at the end. And we can achieve this by a cleverly designed cable, leverage, and pulley mechanism. So we have our spring with linear increasing force connected to this lever, and the force F2 is then actually not linear increasing, but constant over the whole elongation of the spring. And that's because of this leverage which changes. We built this mechanism a second time to achieve the inverse of this curve, and therefore have exactly what we need. And by this, we can obtain a lot more work than before. This is our first vehicle we built by this. It's here. And here's a video of it working.
You have 30 seconds left in your presentation.
Contracts and expense, but we have a problem. The wheels don't really work. So we switched from this ratcheting wheel to a switching and sliding wheel that is better for almost all surfaces. And with this wheel that slides forward and sticks backward, we made another design, which is this. And this actually works really, really well, like you see. Yeah, please demonstrate. We even let it climb up hills and calculated the efficiency, which is about 0.5%. So in the end, we solved the problem, we developed this video.
Thank you for your presentation. And now we will be moving on to clarifying questions from Team France. Yes?
Yeah, please.
I have a question. So, what temperature difference did you use for this to get this elongation?
For the
for the average speed.
So we used a temperature difference of 20 degrees in all our experiments.
Okay, please stay concise. 20 degrees. Yes.
Okay, so thank you. Yeah,
yes.
Please.
What are the dimensions of your device?
So our device, as you see it, it changes dimensions, right? So, but it stays within the height of 10 centimeters and the length of approximately 14 centimeters. But you can, okay, I will explain later more, yeah.
Okay. Thanks.
Yes, please?
Can you go back, please, to the slide with the force and elongation, please?
The graph we measured?
The graph. And how much heat and how much time of heating did you use to achieve this this graph?
So after we let it stretch, we heated it for 2 minutes at a constant rate to achieve a temperature of 40 degrees. And we did it by using a constant current power supply and then kept it going for, so the temperature stays the same for all this time. And after that, we cool it down.
Any further clarifying questions?
The one where it's repeating?
Okay, time's out.
Time for the preparation time of the opponent.
Oui, regarde. Entre quoi et quoi? Entre Martin Side et Austin Side. Martin Side et Martin Side, ok. C'est des types de phrases particuliers, genre comme celui de Liquidias? Ouais, enfin, c'est des structures cristallines.
One and a half minutes left for the opponent. One minute left. Forty seconds. Thirty seconds. Ten seconds, please, all the teams go back to their seats. And let's start.
All right, so thank you very much for your presentation. I think we were all very impressed with it. So just to restate the problem, we needed to make an autonomous device that used thermal expansion. So it should work in the shade and not exploit any temperature difference between the device and the surface that it's on. Moreover, we have some certain constraints, such as the fixed maximum linear dimension of 10 centimeters. And we also needed to maximize the speed for our outdoor weather conditions. So, first of all, to review a bit your presentation, or to summarize it at least, you started with a very qualitative explanation where you explained how snails moved and how that inspired you. You explored different possible ways of making this device. So with the thermal expansion of solids, of gases, you showed the cycle for mechanical work, and you actually calculated this work for the different solutions you proposed. And you showed us the mechanical transmission part that was behind your device. As a quantitative model, you explored the coefficients of thermal expansion, and thus this in the validity domain of the temperature of the transition of the shape memory alloy. Experimentally, you showed us different setups to measure the work and the displacement. You varied some parameters with varying temperature, of course, using different designs such as active and passive springs, and you showed us the different wheel designs. For the theory, you verified it by calculating efficiency and your different observations. So for the bimetal deformation, friction, and the hysteresis cycle for the nitronol coil. So now moving on to the different strong points and weak points that we found in your presentation. So we really enjoyed the interactive presentation of your device. We thought it was a really interesting choice for the propulsion mechanism. And we liked your state-of-the-art or overview of some possible answers. However, we thought that it was lacking in some points. For starters, you didn't really verify or validate the, experimentally, your theoretical data that you showed us. Also, one big discussion point is the fact that shape memory alloys is actually not thermal expansion. It's a phase transition between austenite and martensite. You also, in your overview, didn't explore liquid expansion. We're going to go back to your slides afterwards, but we saw that liquids did expand more than solids. And also, you used very high temperatures for the spring. One a bit maybe petty criticism would be the length of your device that is actually 14 centimeters long, and that doesn't fit in the 10 centimeter linear fixed linear dimensions. So, moving on to the discussion points, we'd like to take some time to discuss about maybe how we can make the device smaller to fit into these linear dimensions, how you evaluated the friction and how it plays a role in the efficiency of your device. Of course, explore liquids, their thermal expansion. Maybe talk about the shape memory alloys and the phase transition that it implies. Talk about mechanical reduction, because you used a bit, but it didn't seem, it seemed like maybe we could optimize your device in that way. And also avoid the hairdryer convection and the way that it impacts the motion of your device. So maybe we can start with the thermal expansion of liquids and why you decided to not explore this route.
So during the time that we were exploring different concepts, we had the three ideas.
You need a mic, please.
Here.
Thank you.
During the time we explored different concepts, we had these three ideas you saw in the beginning. But as we thought of liquid expansions, we also were already working on this shape memory alloys. So we saw that the potential was much greater for this kind of mechanism. And that's why we didn't fill up our bottle, for example, with a liquid. But we thought about ethanol being quite good at this, because it has a quite high thermal expansion coefficient, but it also evaporates, and we had different effects on our materials, so we didn't go into that further. And if I am allowed to, would like to make a small correction. The device we actually built, this one, the newest device, is in every linear dimension under 10 centimeters. I made a small mistake. This is the one I was talking about, and it's, as you can see, much larger.
Even when fully expanded?
This is the fully expanded stage, and you can see
just contracts.
It contracts, and even though it gets larger in height when contracting, the height, as you can see, I don't have two hands free right now, but stays under 10 centimeters, just to make sure.
Okay.
Thanks.
But what made you choose the shape memory alloys rather than, well, because it's out of the scope of the problem, because it's not exactly thermal expansion. How could we maybe use some devices that are based on thermal expansion to achieve the same results, and maybe perhaps even better ones, such as devices that could move more than their actual length during a cycle?
Mm-hmm. So I actually would love to talk about different concepts as well, and different methods to do the propulsion. But we have also came to the conclusion, we thought about this as well, and thermal expansion isn't, it's still thermal expansion with our nitronose spring, because it's just defined the change of length, over time, over temperature, sorry. So,
but I mean, in the thermal expansion coefficient that you showed us,
yes,
it was it's a thermodynamic coefficient that doesn't imply any phase change.
Oh, it actually can imply, it allows for phase change, the thermal expansion. If you look up the definition, and there's nowhere where it's stated that phase transitions are not allowed. So.
All right. So maybe moving on to the mechanical reduction and the way we could optimize this device, because, I mean, as you showed, it moved by 4 centimeters, was it? 43 millimeters?
Yeah, 46 millimeters for the unrestricted,
how could we maybe imagine a way to fully use the force that is output by this device to optimize its speed?
Ah, yes. Could I maybe bring up back my presentation again? So, So this is one of our earlier designs, which used also nitrile, but not wrapped up in a spring, but in a cable. And therefore, we can stack it by rolling it back and forth about these rollers. And what it does is also moving a lever, like this front part, back and forth. But the lever then connects to another cable, which has a submission. So you have a gearing ratio, and the wheels actually turn. And by this design, we hoped to achieve a larger distance, even a larger one of the 10 centimeters.
Did you actually, I mean, I see that you made a prototype. Why didn't you use it in your final device? Did it, were there any problems with it?
Yeah, that's a great question. So we have, we all built this in our students' rooms. And
Thank you. That is all for this discussion. Now it's time for clarifying questions from the moderator. Yes?
Yes, always with the mic, please.
Okay.
You should have tested it.
Yeah.
Could you go just to the last slide before the conclusions, please?
This one?
Okay, this one, thanks.
Could you please explain us the asymmetry in the wheel?
I could explain the wheel again? Or?
Yeah, the wheel, how it...
yeah, of course. Yeah. So...
You should take a mic
we have, oh, I'm sorry.
to answer. And keep it, technical.
So we have two types of wheels for different surfaces. One that actually rotates and one that transitions from a sticking to a slipping phase, actually. So we have different coefficients of friction. This white part slides easily over the first surface, and the rubber part is sticking to the surface. This is the not completely turning wheel, but it only switches from these different materials to another. And because we have three, we can stick the ones on here while sliding this one forward. And when it contracts, the opposite happens.
Could you go to slide 14?
Of course.
We don't have time for any more. Now it's time for you to prepare.
Je suis d'accord.
20 seconds left for the moderator preparation.
Yeah. Une manière de réduire.
10 seconds.
Ils ont proposé un truc avec des poulies et des roses.
Okay, let's begin. You need a mic starting now. Please, everybody, go back to your seats. The moderator presentation is starting.
Okay. Hi, I'm Nicola from Team Politecnico, and I will be the moderator for the problem 17, thermal snail. So the problem asks the reporter to design a device that can move exploiting the temperature fluctuation during the day without using, for example, piezoelectric or electronics. But it also asks to maximize the velocity of the device. So the reporter made a very well work on clarifying all the path that he has made, discussing all the possible design he thought about, and arriving to the final design that actually works, and this is very impressive from my point of view. He also this clever solution was about the shape memory alloys that have a specific properties of transition from one phase to another phase. He also explained why it was necessary to use also a traditional spring in addition to the particular spring made of this shape memory alloy material. And he also showed a very genius way to design the wheel of this device that used two different materials with two different friction coefficients. On the other hand, he didn't explain very well the dependence of the change of phase of this material in relation to the temperature, because he stated that there are different, this device can work at different temperatures, but he not told us deeply why is this so. Because it's very important, because we need a device that can move, for example, at temperature like 20 degrees or 30 degrees. And also he didn't point out which are the limitations of his device. For the opponent, he made a very good recap of the whole process of the explanation of the reporter. And he also pointed out the missing theoretical approach that maybe the reporter didn't have time to explain. He also simulated the presentation of another design in the final part of the discussion. On the other hand, he tried to focus on technicalities like the fact that the system exploits a thermal expansion rather than like it's a thermal expansion in the end, because also a phase transition is still a thermal expansion. So he could maybe focus more on other aspects.
The discussion is beginning.
I want to discuss about the fact that this device can probably have a threshold of temperature. What I mean is maybe it needs some change in temperatures because it can actually start to work. So if you can discuss about this point, for example, from the reporter.
Okay, so in this case we used nitinol, and it was not that easy to obtain because it's not something you buy in a hardware store or something. So we looked up in the internet, and the most available source was actually the wire for dental bracelets. So the activation temperature got tuned by the manufacturer to fit the body temperature of humans. So that's why we have a temperature range between 20 and 40 degrees. But actually, the composition of nitinol can be easily tuned to have a very low or a very high activation temperature.
Okay,
so
this answers my previous question in the previous part, but can we now focus on the existence of a threshold? So, for example, if I increase the temperature of the system, it starts immediately to move, or it takes some certain variation before it starts to move?
Some temperature variation, or?
Yeah, like a threshold. So, for example, if it are at 20 degrees, if the temperature changes like just a bit, it starts immediately to move, or it takes some difference of temperature to start to move?
Maybe if I can chime
in.
I think that there's actually, well, as you say, a threshold, because it is phase transition. So, for instance, if this is the percentage of austenite and this is the temperature, there's something like this. So there's this whole range here during which there is the change, but the rest of the temperature gradient is not used.
Yeah.
So I think that this might be interesting to maybe find a way to exploit this range that isn't maybe fully explored here. And I don't know what you think about that.
So we had materials, data sheets with different, they call this threshold. I think threshold is only one value. I mean, the difference in these temperatures, I would call them like hysteresis. Temperature hysteresis to make the device work. And the hysteresis is around 30 degrees for normal nitinol, but by adding copper to it, you can actually decrease it to almost 20 degrees, and that's what we have here actually. So there are other metals you could add to even furthermore decrease this threshold, but we weren't able to obtain any of these samples.
Okay, thank you. Now I want to discuss about the maximization of velocity, because it was a point of the problem, but I didn't really catch what was the process of maximization of velocity. So if you have ideas about the parameters that can be optimized, then you can discuss about this.
So if I may, I would first define velocity, because we have fluctuations over day and night, right? We don't need this to go like 20 kilometers an hour, because we only have one cycle per day and night cycle. And that's why I would define velocity by the distance it moves over a cycle, and not by over time, yeah.
Okay, so you...
Maybe if I can chime in.
Yeah?
With this definition, you're capped by the size of your system, if I understand correctly, because it cannot move by more than its own length.
That's a great question. I thought this at first, but actually you could, for example, make the wheels turn. So instead of making actually this move like a snail by the whole mechanism expanding and contracting, then you're completely right, we can't exceed 10 centimeters. But if you have cables that drive the wheels, like a lever that will move the cable being on a wall that drives the wheels have a larger radius than the wall, so we have a positive transmission ratio. We could move it further than 10 centimeters in one cycle.
And in this configuration, we could also maybe make use of mechanical reduction with the wheels turning. Like you could maybe imagine some gears that reduce the initial contraction of the spring into maybe bigger displacement for the wheels.
Yeah,
for example, we could make the axle of the wheels turn more than the actual displacement of the spring.
Yeah, that was what I was describing before. I don't, sorry if it wasn't not completely clear, but the thing you mentioned, like in the beginning, the spring is more powerful, right? Yeah. That's why you want to have a positive reduction ratio. That's beautiful, I love this. But in this case, we came up with the solution of this cable mechanism. I can show you here. Oh, wait. This one, which actually transfers this increasing force of the spring or decreasing force into a constant force, because this point, F2, P2, is the one down here where we drive the vehicle. So we actually managed to transform this changing force into a constant driving force. So we account for that, yeah.
If there are any questions from the public?
Well, I have a question.
Maybe
Mike, yes, please.
Thank you. So I have a question about the design you chose, because you seem to consider that phase change is thermal extension. So why, if your goal is to increase the volume between small temperatures and large temperature, why didn't you use like small boiling points liquids in order to create vapor, which would take an enormous amount of volume and just make it way more efficient?
So we thought about this too, and besides from multiple technical difficulties, we also have like a quite small vapor pressure. So if we want to obtain any work from this, the pressure, like for example, due to the piston, increases and the liquid will condense again. So this is, we like compared it, and this is the more reliable option, if you want to say like this. And besides this theory, we also have technical difficulties with things being completely airtight. So we thought even if it works 1 or 2 cycles, maybe the seals were not up to the challenge of multiple days. So then your system would break down. That's why we didn't use it.
Okay, we have another question, so I think he answered correctly.
I'm really impressed with your design, actually. Oh, okay. I would just like to ask you, because probably you're the one more familiar with the design, what do you think is the weaker aspect in your design or in your whole process, and what do you think would be the first thing that you'd try to optimize? Maybe the material, the design, the size. Does the size have any influence in the velocity?
Yeah, great question. So we came from building big prototypes like this, because they're more easier to build, to a small one that fits in our fixed volume. And then we try to simplify it, because the most elegant solution for me is the most simplest, because so there are not a lot of parts on here. But obviously, yeah, like you have a lot of space in here still left, and the spring doesn't even fill up 1% of something of the volume. So you could actually put more of this active material in there, or use more of the space to do it more, to give it more speed or something like this. But it would be also more complicated to explain here. So.
Okay, if we have another brief question. Otherwise, I want to thank you, both the reporter and the opponent, for this really wonderful conversation about this incredible device. Thank you.
Concluding remarks?
From the reporter.
I actually loved the discussion, and would also love to discuss with you further about all the ideas you came up with. And I'm glad we have some similar but also very different ideas to solve this problem. And I think in the end we came up with possibilities to maybe fill up more space, or to build a mechanism that even works faster than this 5th prototype. But yeah, I think finally this problem is kind of solved. Thank you very much.
And now it is time for questions from the jury. Anastasia, would you like to start?
Yes. want to double check. Are we allowing this short question, long question concept, or just one question per juror? Your chair's choice.
One question per juror.
Perfect. Then question to opponent. You were mentioning the reduction for a couple of times. I didn't quite get what you had in mind. So the spring has some like displacement, linear displacement, and the reduction means that the wheels makes longer, I don't know,
well,
displacement, like if converting to rotational one, or what?
Yeah, that's the main idea. Here, with this device, as it is, it's not exactly possible to do it as it is, but we could maybe imagine another device in which the wheels are actually driven by an axle instead of the spring directly acting upon the wheels. And in this sort of device, we could introduce some gear reduction, for instance, by beforehand turning the translational motion of the spring into rotational energy. That we know we can transform easily to either reduce it or maximize the speed.
Okay, I see. Thank you.
Christoph?
I would like to ask about testing the concept in real-life situations. Is it? I mean, the design that you created, would it work outside in a sensible climate zone, and is this the design wearable? So, how many cycles can it go without losing its properties?
So the material itself can undergo thousands of cycles before it starts decaying in some way. And we also, for this, we thought about this as well, like a snail works outside with sun and weather and everything changing. So we made this demonstration where we had like a really sticky ground. This is actually double-sided tape, freshly peeled, so the wheels stick really well to it, but the force of the spring is actually so great, it takes a longer time, but it moves forward still. And we also tried different slopes. Maybe they could be interesting as well. Like this, 10-degree slopes, where it still managed to climb it up. We only had to slightly modify the design by this needle, and then it managed to climb this up as well. And yeah, does this answer the question, or is there more? Okay.
Omar?
Please use the mic.
Use the mic.
Yes.
Oh.
A short remark.
This?
Yes.
Yes.
Okay, so in the part of the problem statement about maybe different zones on the Earth where this would work, the transition temperature can be tuned between minus 200 degrees Celsius and 110 degrees Celsius. So one would have to find a different material or use a different material composition for each part of the Earth, but it will be possible in each part of the Earth. At least if the temperature difference is larger than the hysteresis, which 20 degrees, I think most parts of the Earth will do that between day and night.
Yeah, we calculated for
Okay,
Switzerland.
thank you. That will be all.
Sorry.
Okay, thank you so much. I would like to know something about the angles. What is the reason for the design using these angles?
Okay, we use these angles just to show that there would be leftover force to accommodate for any roughness of the surface or friction that we would need to overcome in different parts of the outside world, for example. So, yeah.
Any graph? Any graph to show
like
your design?
No, we just tested it on different slopes. Like 10 degrees was one that still worked.
Okay,
yeah.
Thank you.
Aurelio?
First of all, I want to thank you very much for the nice solution presented to the problem. My question is related. If you were able to have a material that could solve the problem in, for instance, the known materials that have this kind of shape alloy metals, which one would you use, and what could be the improvement over the system?
So if I would not use shape alloys, but
no, the thing is, you mentioned that you were only able to get from internet this nitrile alloy, but I am asking you if you know or you have looked at another materials or another kind of material. So is to know what is your knowledge about this kind of materials.
So if I would be able to tune the temperature and also the activation temperature of this material, I would try to decrease the hysteresis, of course, and look at the temperature fluctuations of where I am, in like which country, and find out which temperature range would, which activation temperature would be mostly present in a year, for example. So for Switzerland, it would be with from 13 to 33 degrees, we would have 6 times where the temperature fluctuates over these thresholds. So we have six cycles per year with 20 degrees of temperature difference, for example. And if I would be able to tune the material even more, I would also do different activation temperatures. So mechanical systems that not work synchronous, but also add each other, like multiple activations per cycle.
Thank you very much.
Of course.
Jean-Philippe?
Question to the reporter. First of all, congratulations. I really appreciate, because it's not just the idea of your presentation shows it's not enough to have nitinol. You have several tricks. So on slide 23, I see two forces. One is at 0 at x equals 0. Ah, there's one more graph. And then one F2 is non-zero. Ah, wait a minute. So it's slide 22? Yeah. How can I understand F2 is non-zero and F1 is 0? Where does the F2 come from?
So because of this lever, like this F2 is, so this part, we would, with this line like this, with these angles and at this current state, this lever, we would start here, right about here. But the F2 would be non-zero, even though the F1 would be 0, in the case where the lever is aligned with this bar. So you could have a force pointing in the F2 direction, which just gets counteracted by the bearing here. So the lever would lean like this, and then you have a force acting on this point, which can be opposed by this bearing, even though the force has no, the force on the spring is 0. I don't know if I've explained it correctly.
Okay.
Like, the transmission varies, and if the transition ratio gets to infinity, you can put on the force, even though the spring has no force.
Okay, thank you. Does that answer the question? And then we will go to Nino.
All right, so here's a question primarily for the opponent, but others can chime in if they like, since they brought it up, so the opponent should go first. Anyway, could you please comment on what happens to a crystal structure, primarily a unit cell, when we heat it up, and how that could differ with this special alloy?
So, if I understand correctly, the question, it's how temperature impacts the crystal structure of such an alloy?
Yes.
Okay, so basically the crystal structure is just, well, different points, and when we deform the shape memory alloy, we actually shift the position of these atoms relative to each other. So we go from this configuration to this one, for example, where this line has been shifted by an angle. And when we increase the temperature, I believe what you said was that we go back to this first crystal structure. So with the vibrations of the molecules, well, of the different atoms in the crystal structure that occurs at higher temperatures, we can actually go back to this more stable configuration. This is kind of a metastable state of the matter that we can't go back to without a temperature change, because well, because it has a certain energy barrier that we need to surpass.
Thank you. And now it's time for Julia.
Nice.
Oh, it works.
We can't hear you, Julia.
Hello, hello. Can you hear me?
Yes.
Oh, now it works. I have a question from the opponent and then for the reporter, the same question. So from your point of view, what is the main dissipation channel in this mechanism, because the efficiency is pretty low, and how we can handle with that?
I'd say that the main dissipation channel here is maybe the friction with from the wheels on the surface, because we use the stick and slip mechanism. So at one point we're slipping and, well, there's friction. Moreover, I'd say that's the main channel of dissipation. I don't know how it works on the inside, so I wouldn't try and say.
Yeah, I would agree to you. So the main reason the energy, where the energy goes, is basically in friction here. Yeah, that's correct. But for all of the other designs, because we had such a small change in length, for example, such a small displacement, the main energy loss would be the transmission system that converts this small change of displacement with high force to a large displacement with small force. And that was a pity, because in this case, it's the best way where the energy can go. We have the friction over the surface, but if you lose the energy even already before it in the transmission, it would be really sad. So that's why we went with this.
Thank you. Now it's time for Frederik.
Yes, so at some point the moderator asked what the first thing you would do to improve the design was. I would like to ask the same question to the opponent.
Well, I mean, I'm gonna go back to the subject, but still, mechanical transmissions, I think we could really use some reduction here, because you had a force that was a couple newtons, if I believe so, and I think we can more fully exploit this this force range. Although in this case, it would imply some significant changes to the design itself. But I think that the friction that you mentioned in the transmission would be negligible compared to the amount that we gain in linear displacement.
Thank you.
Now, Christos?
Yes, this is a question to the reporter. Could you use this device modified as an electrical generator?
I didn't quite understand. Length?
If you modified this device, could you convert it into an electrical generator?
Oh, I could convert it into an electrical generator, I guess. But with an electrical generator, all we care is efficiency, right? I would care about efficiency, actually. So this device, as great as it is, it's supplied with an infinite heat bath with the day surrounding air. And that's why it can move this great of a distance. But the efficiency wouldn't be as high as for maybe a Carnot process, for example, in a case where you have a limited source of heat. So I could do it, but it wouldn't be the most efficient one, yeah.
Thank you.
Thank you. And now it's time for the jury to decide their marks.
We have decided that the jury members will show their grades for the first round, but hide them for 1, 2, and 3, so that there is an element of surprise for this afternoon.
Sorry.
Was a lot of fun.
Yeah. Thanks.
Yes.
Unbelievable.
Like when we came up with this, we were so happy because in this case we would need friction for it to work. But then we thought, like, if the surface is slippy, we could utilize this property just to slip, because the device is not much friction force.
Yeah.
And that's where, like,
all the juries decide on their grades? Did all the juries decide on their grades? Okay. Now I will, from my left to right, tell the grades. First, for the reporter, we have a 6, a 9, a 7, a 10, a 9, a 9, a 8, a 7, and a 9. And then for the opponent, we have a 7, a 4, a 8, a 8, a 9, a 9, a 8, a 8, and another 8. And then for the moderator, we have a 6, a 5, a 8, a 9, a 9, a 8, a 8, a 7, and another 7. And now we would ask the juries that give the most extreme grades to give a comment. So the most extreme grade for the reporter is Anastasia.
Okay, so my feeling about this problem is that you built very cute device and you made many nice and creative design choices about how to make it work, but effectively your optimization lied into this flipping this force curve, like from this side to this side, so you maximize the total work you can accumulate through the things. So my feeling of this problem is that you need to build a device which you like maximize the design choices, and then you build a model for your system, and then you maximize also, you tune the parameters to maximize the performance. So it's not only about the design choices, it's also about the parameters, how you apply it. And this is what I've been liking here. It's kind of 2 more components to add.
Thanks. Aurelio?
Thank you. I mean, in my opinion, I disagree with Anastasia because I think that the problem is mainly an experimental problem. Because the main challenge, from my point, everything is personal, okay? It's purely personal. I think that you did a great work. You passed through all the steps, even though a presentation in general is not made in a way where you are showing not your achievements, you showed your failures or initial failures, which build up till you get something which is a functional thing which makes all the criteria for the problem, under my point of view. Of course, you lacked during the presentation the time, because you were excited talking about what you did, which is great, to explain all the things, which was not good. But at the end, with the questions from the jury, you demonstrated, under my point of view, that you had thought, and your team had thought, about almost all the things possible that all your brains together could have thought. So, from my point of view, you did an extremely good job.
Thank you very much. Okay, thank you very much. Now a quick comment about your grades for the opponent. Maybe Christophe, you want to say something?
Of course, for the opponent and for the moderator. This problem is difficult to oppose and to moderate because both the opponent and the moderator is faced with a solution that couldn't have been predicted. So you have it straight in your face and you have just a couple of minutes to decide how to discuss the problem. And what was lacking for me in this conversation was a greater focus on what was actually presented, to the appreciation of the strength of the solution. Because with the opponent, I had a problem about some semantic pettiness, because we spent too much time, I think, talking whether this is thermal expansion or not. Well, this choice was made by the presenter. And then I think that there was too much time spent on proposing to explore solutions different than what was actually presented. Also, I didn't see the benefit of a more in-depth discussion of the theoretical part of the solution. I mean, the memory shape alloys, even though you seem to be prepared to discuss those aspects. I mean, like, I want to say that you didn't justify that direction of discussion properly for us to better understand the solution. And then for the moderator, you had a great agenda for the discussion. Unfortunately, the opponent was a little bit unruly and sometimes changed the subject without permission. So you just, at some points, you just didn't have order on the floor. And I also think that you could have done more to stimulate a discussion between the opponent and the reporter, focusing on the strengths of the solution that we saw. Because I think that too much steam went into technicalities in this discussion. And why am I saying so? Because what the reporter showed in response to jurors' questions, he had a huge appendix of additional experiments that it would be absolutely lovely to explore in this discussion. And I consider this lacking discussion an opportunity wasted.
Okay, thank you very much. Does any other members of the jury want to give some feedback, or are we good? We need to keep it quick, but if you want to give some feedback, yeah, Christos?
So yes, some small feedback to the reporter. This was a difficult problem indeed, and with all mechanical problems, there's the need for optimization. I really liked this process of optimization that was actually shown. A lot of teams usually skip this part, but here it was an integral part of the presentation. I like the discussion that followed, but at the same time, I think I will agree with Christoph that maybe some points were overlooked by the moderator and opponent, and perhaps we were hesitant to touch these subjects. But all in all, it was a very nice beginning presentation for the final, and I'm really looking forward to the next two. Thank you.
Thank you very much. Okay, after this first very exciting round, let's have a 10-minute coffee break. Please listen to me a few minutes. The coffee break is just outside, and you can't come back in this room with beverage or food, so no food or beverages in the room after the break. So a 10-minute break, everybody.
I can recommend having a clock.
begin in a few minutes, so please, all team members, go back to your seats. Okay, attention everybody, we shall begin in a few. And I remind that no hot beverages and other things from the coffee breaks are allowed inside the auditorium. Okay, thank you. So I think everybody is here. No, Team Germany is not.
Team Germany is coming. So in this fight, we will have Team France as the reporter team, presenting problem number 7, smart water. We will have Italy being the opponent, and lastly, Germany as the moderating team. Yes, shall we begin the 5-minute preparation time? You're missing one person, or? Yeah, you can't bring tea.
Come on, guys. Yes.
Okay. Then let's begin the preparation time.
Yes, 5 minutes preparation time.
Is the mic okay? Okay.
You want to begin?
Yeah.
Okay, let's go for the presentation. Yeah.
Hello everyone, today we'll present you the problem number 7, smart water. The aim of the problem is to find a way of computing an NP-hard problem thanks to water. So first we'll have to see what is an NP-hard problem and how can we do such a device with water that can solve such a problem. So to see what is an NP-hard problem, you first have to see what is a decision problem. A decision problem is just a problem answering yes or no. For example, solving a maze, is a maze solvable, is a decision problem. P-problems are a category of a decision problem where the solution can be found in a polynomial number of time related to the size of the instance. For example, you can find your way out of a maze in n squared step when the size of the maze is n. There exists an algorithm for that. NP problem is another class of problems that doesn't mean non-polynomial. What it means is that a solution can be verified in a polynomial number of time. For example, with a labyrinth, if I give you a labyrinth, a maze, and a solution through the maze, you can verify in a polynomial number of time that it is in fact a solution just by saying it starts at the beginning and ends at the end. More generally, all P problems are in NP, as you can see. And finally, NP-hard problems are problems harder than every NP problem. That means that if such a problem is polynomial, it would imply that every NP problem is polynomial. An example of such an NP-hard problem is this statement. Imagine 4 cities in Germany, for example. We want to find the shortest railway that connects those 4 cities. And when you compute it by a computer, we find that you have to add another train station here in order to have the shortest path between those cities. Such a point is called a Steiner point. And finding such a graph is called the geometrical minimal Steiner tree problem, and it is proven to be NP-hard. In fact, its complexity is very growing up. It's n factorial, n minus 1 factorial. For example, the n equals 3, when you have 3 cities, A, B, and C, you can find geometrically the Steiner point S, one with the height of the triangle or the circumcircles. But what is important is the properties that we get from that. No Steiner point will happen if the angle is greater than 100 degrees. That means that the shortest path will be the way around the cities. You will not have Steiner points if the angle is greater than 120 degrees. And the other fact is that around the Steiner point, as you can see, the angle are precisely 130 degrees, and that will be very useful for later. So how can you make a true water-based computer with that? We will use bubbles. In fact, bubbles is a physical object that tries to minimize its surface. Why? Because its potential energy is proportionate to the surface. So, for example, if you put a soap film in the middle of 2 plexiglass sheets holded by pegs, you can see that in order to minimize the area of the soap film, you'll have to minimize an integral, and thus a Lagrangian. And thus, that gives us Euler-Lagrange equations, which is stated here. For example, if you put the 2 plexiglasses parallel with a constant height, the Euler-Lagrange equation stated that it has to be a line, and in fact, in the real life, we see a line. If the 2 plexiglasses make a small angle alpha, the Euler-Lagrange equation tells us it must satisfy this property, and the solution is a hyperbolic cosinus, as you can see here. So let's make an experiment. If we dip in the Steiner tree problem with 3 cities, and we dip it out, what we can see is that because it tries to minimize its surface, it will make an additional point here, a Steiner point. So that makes exactly a computer solving our problem. And in fact, if we compare the solution to the simulation, we find a relative error, where L is the computed length of our bubble, of less than 1%. For the n equals 4 part, we have to add 2 Steiner points, and we see that still the angles are 100 degrees. And we see that the simulation gives us almost exactly the same results. For n equals 5, it's 3 Steiner points. But here, something very interesting happens, because in fact, at the beginning, we had this configuration, which is not the minimal. And when you add blow on it, when you perturb the system, we see that we can get the real minima. So what is happening here is that on the energy plot, we went through a barrier of potential energy in order to get to the real global minima, and not the local one. And you can show, we showed using thermodynamics properties that it is statistically correct that we have more probability of going through a global minima because it has the lowest energy than going to the local ones. For n equals 6, you know the answer, because for n equals 6, the angles are exactly 130 degrees, so it must be the way around, as we saw earlier. Here is another example. We have that configuration, and when we blow on it, for the n equals 6 case, we get the real global one. So on the set of all possible local minimals, we went from one local to the real global. Here is a plot of the relative error we have with this system. In a log plot. And what we see is very great because it isn't evolving exponentially. The error is is less exponential with n. And the error comes from the friction with the plexiglass pegs, and here it is not a statistical error, it's deterministic. So what are the other parameters? So we have, for example, the pegs 8, the surface tension, the number of cities, and the soap concentration. And what we want at the end is a time of convergence of our computer, smaller than the time of life of our bubbles, in order to make the computation work, and a time of convergence of our computer way smaller than a real computer, because we want to be more efficient than a real computer. So for the surface tension and the soap concentration, we have to make solid bubbles, because we will perturb them. And for that, we will just go to the critical missile concentration of the soap plus water concentration. For the other parameters, we have to study the dynamics of the soap film. So we'll just do back and forth between the two configurations we saw earlier. For example, here, I just make an angle with the plexiglasses, do that, do that, do that, and we see that it is going from a coche to a line. And by seeing the minimal point, and when we plot it, we see exponentials. It's exactly like an RC circuit. Here is a log, and from the log you can extract the derivative, which gives us a characteristic time. So here are the equations of our movement, and you can find the value for tau. And for example, here we saw that there is a characteristic time of around 3 seconds. Here is a plot of the characteristic time related to the height of the plexiglasses. Here is the time of life, because it is in fact a really important factor. We see that the life is going exponentially down as we increase the height between the two plexiglasses sheets, which is kind of, it was predictable. And to find a great compromise because we want this to be very big and we want that to be very low, we took h equals 5 millimeters. So to conclude, what we have is an efficient NP-hard water computer. We have an algorithm that we have to perturb the system whenever there is no standard point when the angle is less than 100 degrees, or there is standard points with angles that is not 130 degrees. That is not possible for the global minima. So we know that we have to blow on the system. We have a time of relaxation, of convergence, that is less than 4 seconds. And we have a lifetime of the bubbles, which is greater than 2 minutes. And we know that it is statistically correct, which means that if we do again and again the experiments, we will the most probable outcome will be a global minima. So here is an example of the 13 biggest French cities. Okay, so we have to perturb the system because we see that some things are not going okay. So for example, here we have a right angle that is not possible because this can only happen if the angle here is exactly 130 degrees or more. So we have to perturb the system in some ways in order to fix those issues. And the final outcome we have is exactly the standard point you would have on a computer. But for a computer, such with the best algorithm, for this it would take 3 minutes, and we took 20 seconds. So we made a real efficient NP hard water computer faster than real computers for that specific problem. But we can do more. For example, we can add lakes to our problem by making a hole on the lower plexiglass. That will make the cities connected by a train line, a railway, but the standard point has to be on the plexiglass and cannot be on the hole. But we can also add a local cost. For example, if it is cheaper to construct a railway here instead of here, we can build a device like that in order to make such a contraption. And what would happen if we dip in such a device in the water? We find the Snell law with exactly the same properties, which means that the height you chose here, sinus theta, is the height you chose here, sin theta 2. But we can do more. If you want to add a local cost in general, for example, in the mountains, it's harder to build railways in high height in the mountains. So you have to dip a mountain through the plexiglass in order to make, for example, here, the summit more expensive than the valley. And we can do that. For example, let's do a little game. Let's find the train station in the Swiss Alps. Here is the Swiss Alps. We extract the topography from it, and we dip the mountain inside the PVC by 3D printing the surface. And when we dip in the water, we see that, for example, the shortest path connecting Sion, Andermatt, and Zermatt make a Steiner point exactly here, as you can see. And this is exactly what you get with the railways in Switzerland. And what is that point? That point is a city named Viège, and it is a very small city with only a train station. Yeah. But we can do way more. For example, you can take Earth's curvature into account by making it into a circular surface. But you can do way more. You can solve also easier problems. For example, here we solved a labyrinth, a maze, as we saw earlier, thanks to the Steiner tree problem. To conclude, we make a very efficient NP-hard computer and exploited it way more in order to solve all the problems and simulate the railways in Switzerland.
Thank you.
Thank you
very much.
Now it's time for clarifying questions from the opponent. Yes?
You need to click on the button of your mic.
Is it? Okay. Can you go to slide 18, please?
Yeah.
Okay, so how is the parameter defined? Like, what should you get from the parameter eta?
So eta is the length obtained by the bubbles minus the length obtained by a simulation divided by the theoretical length.
So basically, it's the difference between the theoretical and the
exactly,
actual.
the relative differences.
Okay. Could you go to slide 15, please?
Yes.
So the function that we are seeing is a function that you actually calculated by yourself or found in literature? Or
this?
Whatever. Yeah.
It's a representation.
It's okay. It's not
for the visualization.
Okay, it's just visual. Okay. Could you go to slide 11, please?
Yes.
Okay. And to slide 6. Could you explain, just clarify the first rule about the angle that...
This one?
Yeah, exactly.
If your triangle has an angle greater than 120 degrees, the shortest path will be the 3 points.
Okay.
We not add a Steiner point.
Okay, great, thanks.
Now it's time for the opponent to prepare.
Do you know?
See this.
1.5 minutes left for Team Italy. One minute left. Thirty seconds. Technical timeout, 1 minute added. One minute left. Thirty seconds. Fifteen seconds. You ready?
No, not yet.
Not yet, okay. 10 seconds. Okay, let's begin the opponent presentation.
Great. So, hi everyone. First of all, thanks to the presenter. I think this problem was really beautifully solved. So now we're going to explore something more about this problem. So, as for the problem statement, we were asked to analyze and actually create a water-based algorithm that can solve what it is called an NP-hard problem. So, as a summary of the reporter's presentation, he actually explained, first of all, of course, what an NP-hard problem is, so to let all of us understand what we are facing, what problem we are facing. Then he decided what kind of NP-hard problem he wanted to solve. So in this case, the Steiner tree problem that actually explained and tried to analyze. Then our presenter started to create the water-based computer. So the basically the algorithm that would solve the problem physically. The algorithm was pretty neat, actually, a great job, so really good. And the best part, I think, was the additional costs that he talked about. So after the thorough analysis that he did of the basic problem, he started to add costs to actually evaluate different kinds of problems, of real problems that could be solved with this mechanism. And so the practical applications that were really impressive. positive points of the report were, as I said, of course, the explanation of the physical phenomenon that is underneath the algorithm, so that we could understand what is going on physically before trying to compute the results. He tried to explain the difference between global and local minima, because basically it's the focus of the physical problem, of the physical resolution of the algorithm. And he described all the parameters and the limitations of the parameters. So that was actually a really good point, because as our problem is physical, we need to understand the parameters that actually govern the phenomenon and what are our limitations as we are doing it in a physical world and not in a computational world. And then, as I said before, what I think was the original part, the best part, because he just went over and over finding new ways to solve this problem, to add something to the problem. So really the best part probably of the presentation. As for the points of that could be improved from this presentation, I think that I know that trying to grasp what an NP-hard problem is really difficult if you're not into computationals. But I think that probably for someone that actually don't work in that field, it wasn't that clear what an NP-hard problem, the difference with NP, but I can totally relate to the difficult thing. Actually, yeah, I would like to explore together in the discussion what you did independently and what is actually what you found out from literature and what other scientists do, because I think that is the best part of your work and I would like to highlight it. And then, yeah, I think that about the setup and the experiments, I think you could have tried to automate your setup to just kind of try to eliminate some parameters. For example, in how you take your setup out of the soapy water, how you blow. Actually, you didn't explain how you blow on your system, and that would be something that could be actually developed together. Actually, the main points I want to discuss with you are about the simulations, because you cited some simulations, and I really want to know how you were able to do these simulations and how you compared with your simulations with your algorithm, because basically that's the main point. So how you can compare your analog algorithm with a computer-based algorithm. So I think that would be lovely to discuss. Then, of course, I want to do with you the analysis of the problem of the local minima, because that's, for the physical part, it's the most important part, as the problem with the physical algorithm is that when it finds the local minima, it just states that the problem is solved when it is probably not fully solved. So I would like to explore that, and then I would like to explore all your original ideas and further discuss them.
So may I have my...
So if I may, I would like to start with the simulations, because I'm so curious about them. What did you do? How did you build up your simulations, and how you use them?
So the standard tree problem is a graph problem that is very well known. So I used a program on Python on the library SciPy in order to solve it. I used a tracking system in order to track where the pegs are. I get the center, and then I use the program of SciPy in order to have the smallest path. If you want the detail on the program, is the descent of gradient. Okay.
Yeah, I can imagine that it can be found, but what I want to explore with you is how you used your simulation and how you confronted your simulations with your physical work, with your physical algorithm, in terms of local minima, and in terms actually also of the time to compute. So how long does the simulation have to compute, and how, for example, for larger number of pins, is actually the physical algorithm becoming maybe better as the computational one?
Yes, so the algorithm is the best algorithm known so far, which is the one I used to compute those parts, has a complexity of 7.29 to the power of n, where n is the number of I don't know if it's clear, n is the number of cities, right here. So at a certain point, this will cost a lot because it is exponential as
an NPR problem.
Problem. So for example, here in certain cities, you see that it becomes to be very useful, very powerful, the physical system.
Did you find like a threshold for the number of pins? So when the analytic solution becomes better than the computational one?
It's n equals 13. It's why I show that example.
Oh, okay.
The certain bigger cities, it's n equals
13. Okay, I get it. Moving on, I would like to furtherly explore the local minima problem, because I saw that you solved this problem by blowing on your system. So firstly, how did you actually blow on the system? And then how could you be, through the process, more and more sure about finding the global minimum in your problem?
Okay, so I wanted to avoid talking about blowing. What I want to talk about is perturbing the system. We want to add energy to the system. So we can do that with different ways. So I talked about blowing, but you can, for example, vibrate the tree. For example, here, I don't have the global minimum. I have the squared one. But if I vibrate the system, I give it kinetic energy. We will converge to the real one. So just the last thing, and we will converge. And that can be understood very easily. In fact, if we take the graph of potential energy for such a graph, if we are here and want to go to the lowest path, we have to add kinetic energy. So blowing was a way to show the simplest way of perturbing the system. But what is neat with vibration is you don't need a human to take part into the device. You just slowly increase the pulsation of the vibration, which means that you slowly increase the kinetic energy to the point, and you are unsure that at one point it will surpass the potential buoyer, and that's going through. And what is neat is the friction made by the pegs and the plexiglasses make no oscillation, which means that you will go directly in the next local minima. You will not go past. As you can see, it's not oscillating around a minima. It's just going straight forward. So the path of going from a local to a local of flower energy is irreversible. You can't go backwards.
Great.
Instead of that.
Thank you. Maybe we will discuss a little bit later on this topic. What I want to talk about with you next is the original part of your work. So all the things that you started to add. Actually, at the end of the presentation, you were adding so much stuff. I was like really impressed. So please walk me through it again, and maybe let's focus on something.
So I think I missed like 15 seconds to tell this, but in the conclusion slide, it's all the thing we did ourselves that was not in the literature. So for example, optimizing a physical setup was not in the literature. The tau we found, the characteristic time, was not in the literature, and the parameters dependent of that time.
Thank you. That will be
It's
all.
time for clarifying questions from the moderator. Lisanne?
Start. I don't know if you can hear me. Okay, now you can hear me. Could you briefly explain to me the difference or similarities between NP problems, NP hard problems, and NP complete problems?
NP complete problem are NP hard problem that are NP. NP hard problem doesn't have to be NP.
Okay, thank you.
Okay, if I'm allowed to ask, thank you. What are your sources for many of? Did you use any sources to get the ideas for the experiment, for example, or were they all your own ideas? What are your sources for the ideas for the experiment, for example, or were they all your own ideas?
So the standard tree is very well known, but the thing for the Swiss Alps, so it's very everything I put here. So the idea of the maze is our own. The idea of making local height is an idea of our own.
Okay.
The spherical device was not an idea of our own, so I didn't put it here.
Okay, maybe to the opponent. Are you familiar with a paper called The Soap Film, an Analog Computer by Civil Eisenberg?
Yeah, I mean.
Okay, do you have any other question?
Yes, maybe one.
Yeah?
Just one question. You said like you have a maximal time until it gets...
Please use a mic when you speak. You have a mic right behind you. I showed it to you.
You said that
Okay.
You said that there's a maximum time till it breaks down. I guess it's due to like that soap bubble just pops.
Yes, it's due to gravity. The soap just falls
so
down
like,
until a
so
critical.
you always have, no matter of the size, like after around about 2 minutes, it always like pops and then
Yes,
the
exactly.
experiment is
It
destroyed.
would drain, and at one point it would just pop.
Okay, and yes.
So what's the reason for not lowering the H
What is the reason for not blowing the height?
Because lowering increases the time of computation.
We don't have time for
We had a
Okay.
compromise.
Thank you.
Now it's time for preparation.
Yes. The setup. For large N.
Se ho capito qual è l'articolo, sì, ma lui ha letto tutto il nomone e non...
Strick draus. Better. Wait.
Comment ça, il change?
30 seconds left for the preparation of the moderator. $20 seconds. Okay, 1 minute added to your time. One minute and 30 seconds left.
It is full screen, right? No. Yeah. Can you just make it out of full screen and then back?
15 seconds.
It is full screen. It's done.
Okay, it's done.
Everything's set up, so
Let's
I
begin.
can actually start. Welcome, everyone. It's a pleasure to moderate problem number 7, Smart Water, in this year's final. My name is Lisanne, and I'm representing Team Germany. First, let's go over the problem statement again. We were supposed to build a water-based computer without electronics that solves an NP-hard problem. Just a general evaluation of the reporter. First, I have to congratulate you. I think your setup was lovely. I really enjoyed your presentation. You had a very good structure. You had a good idea to use surface tension of bubbles to create a Steiner graph. I liked that. And you had a very good analysis of the parameters. It's like one of my pet peeves that people don't look at parameters, but you did, and I loved it. You had a nice comparison of the accuracy obtained with your water-based computer and a real computer. I think that really added to the problem. And you had some points I would like to improve on maybe in the next few minutes. So first, you didn't have a live demonstration. I think that's really sad. I would have loved to see it. Second, you didn't really talk properly about scaling, optimization, and your method. And I think all those points really are interesting, so we can see how good your solution actually is. And you didn't really explain your sources, so I had difficulties to actually see which ideas were yours, which ideas were from the literature, and I think that's actually an important point. About the opponent, you had a very good summary of the reporter's presentation. You also caught most of the missed points in the presentation. I really liked it. Also, you had good suggestions what we could improve, how we could continue, but your discussion, I think, was a little bit one-sided, but we can change that in a second. About your discussion flow, first you discussed about the simulation. You compared the simulation to the experiment, and you talked about runtime analysis. That was great. And I think that problem is basically shut now. Then you discussed about the local minima problem and talked about how we could actually be sure if we're in a global or local minimum. And I think we can actually add something to that in a second. And last but not least, you discussed about examples, about the examples on the end of the presentation. I also enjoyed that very much, and it was your own, so yeah. what to discuss next. First, I would like to again look at your method for global versus local minima. So you said you were blowing in the presentation, but you also said you were shaking it, and you didn't really want to talk about your blowing method. But I want to talk about your blowing method, and maybe the opponent wants to too. So that will be our first point. Afterwards, we can talk about if you can reach the global minimum of your problem if you don't know the solution beforehand. And it goes in the right direction, I think. Then I would like to talk about scaling and limitations. So how does your experiment actually behave for large N?
It's time.
And I think that's also something we can start with. Maybe, yes, opponent, do you want to?
Thank you very much. If I can extend about the global minimum problem that we were talking about earlier. So about the blowing versus vibration method, I think that what you were trying to say was that the blowing probably would have been the first and more intuitive method, and then the vibration would be the best one, probably. But I think you could have optimized it by not vibrating it by hand, but maybe with some contraption. So what do you think about that? How could you improve that kind of analysis?
So I think blowing is the most intuitive way of solving the problem. As I said, if your graph does not satisfy some properties, as for example, an angle that goes past a city that is not 130 degrees, we know that it has to be like that. So we know that we have to blow here. But the thing is, that involves a human reflection, and we don't like that. So vibration doesn't need anything. We just have to make a vibrant pot going slowly and slowly, more faster, and we should just reach the next local minimum. And doing that again and again will eventually give us the global minimum.
So what you're talking about is basically annealing, right? So what you would also do with a probe and, I don't know, quantum computing or so on. I think you have a good point, but my question would be maybe both to the opponent and to the reporter, if the vibration method actually works as well, and if you could do it for large systems. Because you showed us for n equal 4, that worked lovely, but I'm not sure about the scale.
What I personally think, if I can, is that actually it is much better than blowing because, of course, blowing is only directional and vibrating actually excites the whole system.
Yes.
And you can also choose the frequency and amplitude of your vibration in order to decide at what point you want to put your energy level on. What I'm reflecting on is how can you find the global minimum with that, actually with any kind of vibration, because the system actually goes from one minimum to another, but cannot detect if that minimum is the global or the local minimum. So you could actually demonstrate the solution of the NP-hard problem with that method, but you cannot find it. I mean, you have to know beforehand which is the global minimum.
In fact, you can find it. It's what I said earlier. Because of the friction, the friction does not allow going to a minimal to a greater one, because you cannot surpass the next potential buyer. So you can doing that, you can only go from a minimal to a smaller one, and eventually converge to the global minimum.
Yes.
If you have a larger barrier of potential and then a greater minimum there, what happens?
It's exactly the same thing. You add vibration.
And you come here.
You can. It's no problem.
So
at that point, you go to the other point. And thanks to friction, you do not gain kinetic energy rolling down.
Okay, so
thanks to friction.
You vibrate between these two minimums until you reach the third one.
Exactly.
Beautiful.
Okay, but one question about that. I mean, you measured all your parameters, right? Do we have actually, you measured all your parameters, what I really liked. But do we actually have, I mean, we have soap, right? If you vibrate it too much, maybe it just breaks. I don't know if the opponent has an idea about that, but I think that's actually an interesting point because you say, vibrate it more and more, and then we always get in the global minimum, right?
Yeah, I think that actually an interesting parameter that we could evaluate is the velocity, I mean, the time scale of the problem.
Yes.
Because if you can understand exactly how the time scale is with different number of pins, so making the problem harder and harder, you can understand how the problem is optimizing the solving process compared to the computational one.
Yes.
I think that was
Yes, maybe we can actually move on. We have also questions, but I would like to pitch the next topic before we get to them. So I wanted to talk about scaling. You showed us n equals 7, right? What about like very large systems? Where does your water computer break down, or do you have an idea about like the limitations of your experiment? And then
I think the limitation of our experiments is the lifetime of the bubbles. So in fact, we saw that for soap plus water, the Marangoni effect will at some point be stable. But we can use different liquids in order to make the bubbles very more solid for a larger N.
But then the question would be for you both, maybe, can we do something about that? Like, how would we change our setup to actually get to a larger N without this limitation?
I think that intuitively, we would have to make the system bigger and bigger in order to have more pins that are not too much close one to another, because if they are all dense in the same volume, in the same area, that would create problems.
The thing is, here you have a compromise, because spreading out the pegs will make more film and make it less stable.
Of course,
So
and that's probably why you have to find the compromise, and you have to find the limitation of the problem, because you need to scale again and again and again until you find that limit where you can say, okay, I cannot use like more than 100 pins or 1,000 pins, because if I use more than that pins, I have to use a large area, and I cannot afford to do that because of the lifetime of the bubbles. Or you could also try and make the lifetime of the bubbles bigger and bigger, like find a resolution for the physical limitation instead of a solution for the computational one.
Exactly. You can increase the parameters each time. Yes, exactly.
Yeah.
That's great. We have a question from Team Germany, I think, and also from Team Italy. I see you. So maybe we start.
I think it's almost in the same discussion as you are talking about. I was just wondering, like, if I have a larger system, I guess I also need more time to vibrate till I'm in the global minimum. So, like, you have some data. Like, did you research like how much shaking I need, like, independence of the size? Because then I think it's quite easy to like get the maximum number of points we can tackle with this problem.
Yes, it comes from the kinetic energy of the bubbles. Here you have the kinetic energy when you input a vibration of amplitude A and a frequency omega. And you see that it is proportional to the length. So if you increase the length, you can allow you to decrease the pulsation, for example.
But if I may, I think that finding the minimums is a real problem, because actually with larger number of pins, you cannot analytically detect all the minimums, even computationally. So actually the computer itself just does the simulation, so it simulates every single kind of perturbation that you can add to the system, and then he finds empirically, if we can say so, the number of minimums, not analytically.
Yes. I think that's an interesting point. We have a question, but just to conclude this, I think it's an interesting point to think about if we actually can be sure about our global minimum with a large number of n.
Stochastically, so
yes,
empirically,
exactly,
you can be sure.
So, can you hear me? Okay. In the slide where you confront the time computations for your analogical computer and digital one, did you consider just the time in which you put the device inside the soap, or did you also consider the time in which that you need to find the minima from the local one?
So the thing is, I wanted to compute the time when I perturb the system in order for him to go to the next local minima. I wanted to compute that. And I used the analogy with the hyperbolic cosinus on the line in order to compute a tau independent of all other parameters.
Okay, so for an iteration, you don't consider the time for the bubble to stick to the pin?
No, I don't take it. Until the perturbation to the next local minima.
That was a lovely closing word. I think we have 10 seconds or so left. I would thank you both for the discussion. I think we had some very interesting points. And yes.
Time for the concluding remarks from the reporter.
Conclusion from the reporter, please. Team Friends, conclusion. Reporter.
Oh, sorry. So that was a very interesting discussion. So we talked a lot about local and global minima, which allowed me to show the result we had stochastically. which was very great. We talked about the limitation of our problem, how it scales up in with respect to n, the number of cities, or the length of our device. So thank you a lot. That was very interesting, and I hope you liked that presentation.
Now it's time for questions from the jury. This time we'll start with Christos.
Definitely.
Yes.
Okay, so I would like to ask the reporter, you find a way to minimize the distance between two cities or more, but on the same time, when there is heavy traffic, this is not the fastest route. So how would you simulate traffic in your system?
I'm thinking maybe with coloring water, maybe. You can maybe colorate one side of the bubble and it would spread out to the other cities. And maybe doing that on all points, you can maybe find a compromise for that circulation problem.
Does the opponent or moderator have a different opinion on this?
Yeah, actually, I think that, for example, you could add a cost, because you can imagine, for example, that you would have more traffic on a road where you would need more time. For example, if you have an highway, it would be much more fast to use that kind of road. So probably you could add a cost, like for as you did with the different heights, because you actually can put at a higher height the road that you would find with more traffic. But I'm not sure if you can predict beforehand which road would be the one with more traffic.
No.
I think
thank you.
we don't have time. But like,
maybe I think your ideas are excellent. I would agree with the opponent. Maybe you could also add something like friction, or some way to actually suck a little bit of the soap out of the way, maybe like a little sponge, however, to actually add this cost. I think that's a very good idea.
Okay, thank you. I hope Google Maps is watching our live stream.
Falek?
Yes, so you told at one point about curvature, how you could simulate the curvature of the Earth.
Yes.
Could you go to that slide and explain it in more detail?
Yes.
Wait, I didn't catch it. Yes, so how does this work?
So you have to adapt the system to the spherical coordinates. So you, instead of making pegs, you just draw a line from the center of the sphere to the points you need, and then you dip it in the water, and it would make a Steiner graph, but in spherical. Yeah. Here is the device, for example. Broke down. Just a thing, it was a live experiment just before it was made here with the camera.
Okay.
Thank you.
Julia?
I have a question for the reporter. Can you quickly, to sum up finally, what is your criteria for finding global minima? Like when a local minimum become global enough?
To find the global minima, you can just dip out the device horizontally, and stochastically, the one with most probability to appear is the global minima.
So when your criteria, when you think this amount of shaking is enough?
So there is no shaking here, but shaking make it even more often, make the global minimum appear more often. Shaking is just a way to make the probability of the global minimum appear more often.
Okay.
No, I didn't get that, thank you.
But you have to repeat the thing, because it's stochastically the global minimum. Even with vibration, you have to repeat the experiments. The vibrations that just make the global minimum more probable to appear.
Yeah, until what moment? When you see this is not local minima, but it's already global minima?
Because it is stochastically, you just, if you want to shake it at a certain amount of time, you can...
Okay. Nino?
All right, so that was exactly the question I wanted to pose. And I see the opponent and moderator are raising their hands, so maybe they want to chime in on the discussion.
Yeah, basically, from my part, the thing that I want to highlight is that there is not a precise way to find the global minimum. I mean, you can do it stochastically, as you said, so it's a question of probability. You are never sure in your physical problem, in your physical algorithm, you are never sure that you are in the global minimum, because basically it is not memory. So he finds all the minimums, but he cannot compare them, and he cannot find the global one, so the one with the least energy.
I would definitely agree, and maybe add that in this kind of potential it seems straightforward, but if we have a more complex potential landscape, then maybe our global minimum is just very, like only a little bit deeper than all our local ones, or even worse, we have a very deep local minimum, but there is actually another global one. And I'm also convinced that you can't tell when you have to stop shaking experiment or blowing or whatever you do, because if you don't know already the solution to the problem.
Or at
You don't have to know already. It's just you measure what configuration you have, and the most probable one will be the global minimum.
I mean, yes, stochastically you are right, but
is using. Okay, I think this is too much of a discussion. Let's go to Jean-Philippe.
I'm sorry, but I'm continuing on the topic. I understand you want to replace, I'm speaking to the reporter, you want to replace the blowing with shaking. How do you want to turn off the shaking to get to the minimum? It's really a spin glass type problem. So it's, to me, it's totally non-trivial to do the annealing and then cool down and get to the minimum.
The thing is, you increase the frequency at a point where you go through the highest potential Boyer in order to get to the global minimum. And once here, your energy is not enough to go through the next potential Boyer. And this comes from, it's very specific to that problem. This comes from because the energy is proportionate to the length of the system. And because the length is minimal to the global minimum, you will not have enough energy to go through the two next potential Boyers.
Okay. Aurelio?
Yeah, thank you very much, the three of you. My question is also elaborating more with this discussion. And my point is, if you have thought a way to improve the convergence towards the best or global minima by changing the diameter of the pegs.
The diameter of the pegs is very useful here because it's what gives friction to our device and thus avoid passing through minimums. So we still get. So I don't want to improve that point.
Okay, but what is your feeling about it? So what happens if you increase the diameter? What happens if you decrease the diameter?
I think the more diameter, the better, I think.
The more diameter, the better?
The better, because it would increase the friction, and thus you cannot go surpass one local minima.
Okay, thank you. Omar?
Okay, thank you so much for the fight or the discussion. I would like to know something about the entropy of the system and how it's connected with the resolution of the NP hard problems.
So, for
just a brief comment for the report, for the opponent and the moderator.
Okay, so the entropy is a thing very well defined in computer science. And it is exactly what we have here. It's like the same definition, the sum of the probabilities log the probabilities, and it allows us to find the global minima in such a minimization program. So the use of the entropy in physics is the same, if I understood your question, in computer science.
Please use your microphone.
Because you have to maximize the entropy, this gives us an equation that guarantees us to have the highest probability for the global minima. It's the maximization of the entropy that gives us the results we used in the presentation.
And the relationship with the empty problems?
With the?
The relationship with the, when you are looking for a minima using an entropy measurement, what is the relationship with this approach to find the solution for an NP problem?
I think it's a classical approach for all NP problem, if I understood well your question.
Okay.
Yeah, basically to answer this last part, if since you're answering the question about the Steiner tree problem, which is an NP-hard problem, and the NP-hard problem is actually describing a class of NP problems that can be related to that one through a transformation. Basically, you are answering, you are studying the NP-hard problem. So if you can relate the variation of entropy to this physical problem, you're basically making the relation with an NP-hard problem itself, since the Steiner tree problem is one, and then you are relating it with all NP problems of that kind.
Okay.
I must say I'm not completely sure, and I'm not completely sure if I understand the question right. But if the question is if entropy is an NP problem, and
no.
I don't know. I'm actually curious. I didn't really understand the question.
Yeah. Do you know what is entropy?
I'm sorry. We
should know what entropy is, but I'm just
Christoph, can you ask your question, preferably short?
So I'd like to see the slide with the 13 French cities, please.
Sorry?
The slide with 13 French cities and the optimization.
Yes.
All right, so you introduced the error measure, which is the difference between the length of the film with the length of the minimum, and I'd say that the graph that you obtain is either correct or not. So then I would love to understand the accuracy of your solution with respect to this discrete measure, and if the comparison that you are making in this slide that your water computer is better than the analog computer in solving the Steiner tree problem for 13 points involves human-assisted blowing, or this is just with a random shaking of the board?
So for the second part, the human blowing approach is the most intuitive. It's the one I used in the presentation, but it involves a human. So the vibration works exactly the same thing, but it's not local. It's what is even better, because all minima will happen at the same time. The flow of the...
With the time scale 2?
Sorry?
With the time scale 2, because you said that with blowing you got to the correct solution in like half a minute. Would it work on the same time scale with
yes, exactly. It's the
shaking?
same case of going from your configuration to the next local minima. Okay. It's going through the slope.
Okay, thank you. Anastasia?
And I'm not going to ask you about local minima. So when your scenario with the curvature, I understand that the pin's height was defined through the trade-off between the breakage and some other thing. When you have a curvature and the tops of your pins are not actually not on the same line on side, so it's like curved, and this is like short pins here and there. I reckon it's another factor which is limiting you, how you're thinking of approaching it.
So you're asking if it's exactly the same problem with the spherical...
What we need to do if we have too far pins on the curve plane.
So for the curvature, it was just an image to show how far we can go to this. I haven't tried going, for example, with 3 points exactly on the sphere, because it's complicated to make it up. But I think it will work perfectly fine, I think.
Okay, thank you. Thank you. So I will remind the juries, we will not show these grades, but you have some time for grading your marks. And then afterwards, a few of you can come with some feedback.
It was.
Okay. Can we have some quiet, please? We will ask the jury members if they have some very quick, please, feedbacks to give to the team members. So please don't reveal your grades if you give some feedback, but we have time for 2 or 3 remarks if any one of you wants to give one. Yes, Christophe?
I would like to say a few words about the presentation and the moderation. I'm going to use a slightly playful language. Don't feel offended if it's too playful, but your results to me are like a dessert before the main course. I mean, your experimental setup is phenomenal, and you could explore the possibility of increasing the number of pegs in a going beyond the limits that I believe that are available in the literature on this problem. So you actually stopped at some point, and I didn't understand why. Also, Duta says that the thinner the pins, the better. Now, I have a comment about the moderation, and I really enjoyed how Lisanne overstepped her role of the moderator, and for a couple of seconds, a couple of times became the second opponent, and this actually put the discussion back on tracks wherever it strayed aside. So I would say that this was a risky gamble, but I think that it worked very well for the discussion. For the opposition, just 2 words. Very good.
A lot of emotions.
Okay, thank you so much. My comment is for the reporter. You guys made an extremely great job with this approach to solve the problem. But we don't forget that always all the work that we do nowadays is in the shade of the giant. So it's necessary to give the acknowledgement, and all the works that the other people had presented or published will be acknowledged in our work, and present the reference and bibliography related with all, not just the previous one, but also the Steiner work, for example, was well referenced, but related with the ideas that you had in order to resolve the problem.
I think the problem is I lacked 1 minute at the end to explain that the conclusion slide were what we added to the problem. So that's why I explained it on the opposition.
Okay.
I wanted to make a very resume thing to make what is my thing and what is the others. Sorry for that.
Anybody else for some feedback? Or yes?
Jean-Philippe?
Jean-Philippe?
I had pretty much the same comment to make, but it's not to the reporter. It's throughout the week I felt very uneasy about the way literature is cited, and I decided to do my evaluations, including today, without taking this into account. But I think this is a real problem.
Okay. Oh, great. Great. Let's give a final round of applause for this second round. Sorry? Another remark?
Is it a really short? Okay.
Or do you want to give it over the small coffee break? No, really. Do you want to give it to everybody, or? But it should be short. Christos, please. Short. Make it short.
10 words.
Okay.
What an amazing case of a presentation exciting the audience, and a moderator and opponent helping us expand our knowledge actually.
Okay, we grant you a 5 minutes coffee break, so please be back in 5. to the stage. We will begin very shortly. Is every team member here?
Just to make sure.
Okay.
No speaking during the presentation. But
No speaking during. But
Everyone? I don't. Okay. Okay, we're about to begin. For this physics fight, we will have Team Italy presenting solenoid resonance. And for the opposition team, we will have Team Germany. And then for the moderation team, we will have France. I hope this is a good fight. And now the preparation time for the reporting team begins.
Okay. Okay.
Okay. Are you ready to begin?
Okay, hold up. Jeez. Okay, so I'm ready to begin. So my name is Federico. I've already presented myself, and on behalf of Team Italy, I'll present problem number 3. So what happens if a spring is traversed by current? This is the fundamental question we'll be trying to answer today. So the problem is articulated in 3 main points. Firstly, we have to find the motion of the spring when the spring is traversed by current, and eventually find some equations that govern its motion. Secondly, we have to find if there are any resonant phenomena in the system. Thirdly, what we have to do is put the spring in an RLC circuit where L, the inductance, is the spring, and study the system, especially from an energetic point of view. We have to see, especially if there can be energy transfers between the mechanical part of the system, so the spring, and the electrical part of the system, which is the RLC circuit. Okay, so let's talk a little bit about the experimental setup. We had our spring hanging vertically. We used a power supply. We needed great power, as we'll see in a bit, connected to a wave function generator with which we could provide the spring with any current we wanted. And then we used an oscilloscope to analyze what was going on, and especially this was useful for the third part of our presentation. So the analysis of the RLC circuit. So how did we actually track our spring? We used a tracking device, and this was especially good because it was fast, accurate, and especially non-intrusive. We didn't want to perturb the system because the forces at play are extremely small in the order of the millinewtons, so we needed something that wouldn't perturb the system. Now, what's actually going on here? If you take 2 parallel wires to each other with current going in the same direction, then these 2 wires attract each other. So this is actually the key principle at play here. If you take 2 coils, they are both traversed by current in the same direction, therefore no matter the direction of the current, they attract each other. So how did we tackle this mathematically? We used Biot-Savart's law, which is a law that computes the magnetic field created by an infinite wire. This approximation shouldn't be that bad if the radius of the spring is big enough. And then to compute the force between 2 coils, I and J in the spring, we used Laplace's formula. Now, where L is the circumference of our springs. So with these 2 formulas, we obtained the force that coil I exerts on coil J. And notice here that all the key parameters of our system are outlined. And since the forces are so small, this formula is very useful to us, also from an experimental point of view, because we can try and optimize which parameters to amplify and which ones to reduce for the spring to actually move, because this is a very challenging feat. Now, another thing that I want to point out is that the force goes with the current squared. This will be a fundamental result, but we'll try and we'll see how we verify this experimentally. Now, how do we actually model the spring? So we model the spring as a spate of masses connected with ideal springs, so springs with no mass. We wrote Newton's equations for all of these masses. Each mass has 2 spring forces, 1 damping force, gravity, of course, and this last term that accounts for the electromagnetic interactions with all the other coils. So this last term will be a sum over all the other coils. Now, we use 2 approaches to solve the system. The first one is a direct simulation with Python, which directly solves the system numerically. And we use a linear model with MATLAB that introduces more approximations. I will not present this. I'll only talk about the direct simulation, but maybe we can expand that later. So this is our simulation. As you can see, the spring is there, we can visualize it, and we can visualize how it's moving in time. Now, the last portion of the spring. Now, this was our real spring. And as you can see, it's comparable. Now, one important remark that we have to make is that since the force goes with the current squared, the frequency of oscillation, of mechanical oscillation of the spring will be double the frequency of the current, because a sine squared is a sine with double the frequency, plus an additional constant term. Now, to verify this, let's take a random sample from our data, and we compute the Fourier transform of this and find a peak at 1.2 hertz, where this sample was computed at, with the current frequency at 0.6 hertz. So this is a first very important experimental verification that the force goes with the current squared. Now, let's compare the simulation with our experimental results. The first thing that we can do is fix the current frequency and vary the amplitude. Now, our amplitude current was on the order of 5 amperes. So this is a very big current in order to actually see these results. So this is the result of our simulation. As you can see, it's quadratic, this makes sense since the force goes with the current squared. And comparing this to our experimental data, we get that the fit is pretty good. So this is another confirmation of the fact that the force goes with the current squared. Now, another thing we can do is fix the amplitude of the current and vary the frequency, therefore computing the spectrum of the current, so its response to any frequency. Now, this is the result of our simulation. We can see 2 resonant frequencies, one larger at 0.5, 0.6 hertz, and another one at about 2 hertz. And our experimental data is actually in very good agreement with our simulation. So we have 2 peaks at around 0.5 and 1.85 hertz in that case. Now, this is due to the fact that the parameters we measured are not exact. The resonant frequencies actually depend on the elastic constant and the mass of the spring. So let's now talk about the RLC circuit. This was probably the most challenging part of our project, of our problem. In order to describe this type of system, which is comprised by an electrical part and a mechanical part, we need a system of coupled differential equations. So one that describes the electrical part and one that describes the mechanical part that are coupled. So the first equation we write down is the equation of the standard RLC circuit that relates the potential given by the generator to the current in the circuit. The second equation we write down is a simplified model of the model I showed before that only takes into account the last mass. So x is the position of the last mass. The third equation actually couples the 2 above equations, giving the relationship between L, which is the inductance, which is proportional in an infinite solenoid, to 1 over x. Now, actually, x is the perturbation from the equilibrium point. And x0 is the initial position of the spring. Now, what can happen in the system? The first thing that can happen is that the resonant frequencies of our spring are uncoupled or very distant from the resonant frequencies of the RLC circuit. In this case, there's no coupling between the 2 systems, which are basically independent from each other. The second thing that can happen, which is actually way more interesting, is that these 2 frequencies are similar. And this is the condition to be met in this case. Now, in this case, we actually have 2 additional terms in the above equation for the RLC that take into account that the L in the inductance is variable. Now, how do we obtain this? Well, as you can see, one way we can do it is by increasing the capacitance. So what we did is buy a very big capacitor. 400 farad is not a joke. Now, let's see, we computed the Bode diagram of this circuit, which basically gives the answer of a circuit to each frequency, the gain of a circuit for each frequency. And our results, experimental results with the oscilloscope, are in agreement with theory. But this is not what we want, because as you can see, there is a plateau. Therefore, there isn't a specific resonant frequency in the circuit, but this plateau extends 10 orders of magnitude, so it's huge. This is a logarithmic scale. What we would want, what we would really want is this type of situation. And to obtain this, we need this critical damping coefficient, which describes the damping in the circuit, to be lesser than 1 over the square root of 2. This is a well-known result that I will not discuss theoretically, but we can maybe get into that later. But basically, what we want from this, what we get out of this, is that the L, the inductance, needs to be raised. Raising the capacity doesn't work. So these are values that work for our system, and actually it's incredibly challenging to increase the inductance because the magnetic fields that the spring creates inside of the solenoid are extremely small, so we would need a ferromagnet, a very soft ferromagnet to actually follow these fields. So what we rather decide to do is provide a qualitative explanation of what we think might happen to the circuit if these conditions were met. Now, consider an RLC circuit at rest where everything is turned off. If you turn on the generator at the resonant frequency of the circuit,
30 seconds.
We expect the current to go up. Now, the current goes up, so the length goes down, and the inductance, therefore, goes up. This causes the resonant frequency of our circuit to change. Therefore, we're no longer in resonance, and the current goes down. Now, in this case, we have high mechanical energy and low electrical energy. We can loop back and get the other situation. Now, in conclusion, when asked the motion of the spring,
Thank you very much. We don't have time for a conclusion. Okay. I'm so sorry. Okay.
Well, thank you very much for your attention.
Now it's time for clarifying questions. Lisanne?
Please use your mic when you speak. You have one right.
Could you please go back to slide 8? Was a question.
Yeah.
Okay. Here we go.
Maybe one slide further, where you showed your experiment next to your simulation. Back.
Slide 9.
Okay, here.
Yes. Okay.
Oh, can you please play the left picture?
Yeah.
Oh.
Okay, here it goes.
Okay. Okay, and do you also have the same thing for your real spring?
For my what?
Like you compared, I think it's not a clarifying question, but do you have the same graph for the actual
The real spring?
Yes.
Yes, we actually, with the tracking device, we found the position of the
Please
last
keep it
mass.
short. These
Okay,
should be
thanks.
technical
So
clarifying
this is an
questions.
example.
Yes, thank you.
Okay.
Could you show me again the slide where you play ahead the Lagrangian of the spring system?
We never computed the Lagrangian of the system.
Okay. Just another question.
He's a Newtonian.
Sorry. Yeah.
Yeah, go ahead.
Like you simulated it in Python, I guess, and which kind of integrator? Like how did you simulate it? Like which type of integrator did you use for it?
We used a library called VPython, which allows you to model systems iteratively, basically, in each point of time.
So another technical question to your experiment. So which material is the spring consisted of, and is the wire solid or?
The wire is solid, and we use aluminum.
Okay.
Thank you.
Thank you very much.
And now it's time for preparation time of the opponent. right there, Neil.
1 minute left for the preparation of the opponent.
Wir können
30 seconds left.
Ja, nee, lass es nicht riskieren.
Fifteen seconds. Okay, we will be some quiet. Okay, let's go.
Okay, hi, my name is Christian and I'm the team captain of Team Germany, and now I will be the opponent on problem 3, solenoid resonance. So maybe let's first take a look at the problem statement. Let me see here. So we should consider a helicoidal spring with a mass attached to it and pass current through it and thus influence the motion of the spring. And then the questions are, how can we influence the motion of the spring? What happens if we put this system in an LRC circuit, and what kind of resonance phenomenon energy transfer can we get? Especially between mechanical and electromagnetic modes. Ich mach das. So first of all, a quick summary of the presentation. We had a demonstration of the experimental setup and evaluation with the video analysis program tracker, which I think is an elegant solution. Also, there was a theoretical model of forces acting between wires, and thus, also the force acting on the coil by, so they calculated like the limit case of that. Also, they had a demonstration of a simulation of the oscillation of the coil with Python that I would maybe later like to know more about. And they compared the simulation experimental results concerning the amplitude of the oscillation and resonance frequencies at resonance of the system. Also, they did some theoretical modeling of coupling systems with the mechanical and electrical oscillation by having the spring in the LRC circuit, as the problem statement asks. And also, they did a little analysis of the energy exchange conditions and finding parameters with which the coupling system would work. However, about the last point, maybe I think we didn't really go into what kind of energy transfer you did observe in your system, but maybe let's first also look at some other aspects. So something that I really liked was your theoretical explanation of the driving force. I thought it was very intuitive, and also I had nothing to complain about there. And also you performed experiments on all parts of the problem statement, which I think, that has to be done, and you did that. And also I quite liked your model, how you modeled the spring mass system. I think you used something that's kind of similar to a linear atomic chain model, and I would like to discuss more about maybe the resonance that this model provides. Sometimes I was a little unsure what the necessary approximations for these things were. Maybe when we talk about it, you can just quickly clarify. And also, I'm interested in whether your eigenmodes of the system are really sinusoidal, such as a driving force, or whether it's necessary to maybe decompose the resulting motion into the eigenmodes of the system. Also, we didn't really talk about optimization of the spring. You mentioned that you used an aluminum wire. I think maybe that's also something where one could easily optimize and maybe also thus make a more qualitative analysis of the problem or increase the quality of the experiment. I already touched on the missing energy transfer, and I wanted to also talk about the spring model, where you modeled the force of the spring, because you modeled it as wire loops adjacent to each other, which I think it's an interesting solution, but I'm not 100% sure how well that holds, especially in limit cases. And maybe very quickly you can give me some convincing argument on why I should believe this. Just some nitpicking, the error bars on the plots were missing, which kind of make it difficult to see the agreement between fit and theory, but that's, again, just nitpicking. Maybe I should move on to the points that we actually want to discuss about. So first of all, they're about simulating the whole problem. You mentioned that you can create the equations of motion, and if you have those equations of motion, I believe one could numerically solve those. And maybe that would be interesting, and we can look into how one would do this. Also, the problem statement explicitly asks about resonance, so I would like to know what the resonance modes do exist. Are they sinusoidal, or how do they differ? And maybe if we have time for that, we can also discuss whether they can be driven selectively. Also, of course, energy transfer, the problem statement mentioned it explicitly. We want to know how energy transfer works. You mentioned that you had some difficulty with actually getting good resonance phenomena, so I think it's also fine if we look at limiting cases. Actually, the first one was the one that you did in your experiment, so I think you might have some really good insight on that limit case that maybe I would like to get some further insight, especially also with respect to the above topics. And of course, if there's time left, we can discuss how to optimize the phenomenon. For example, I already mentioned aluminum in your coil. I think it would just immediately make it better if that was substituted by copper, but I think this is something that we can touch upon if the other things are solved, because it's not as central to the physical understanding of the problem statement, in my opinion. Okay, so I think time's almost up. Maybe let's get into the discussion.
A very interesting thing, so let me put my presentation.
I think that would be a good idea, yes. Maybe if I suggest a starting topic, can you very quickly give me some convincing argument on why your adjacent wire loops are really equivalent to a spring?
Okay, so first of all, we have two approximations. First of all, we model the coils as actually coils and not helix, basically. So another way you could do this is by solving an integral, basically from the Laplace formula. This is a very complicated thing to do, so we opted for a very much simplified model that basically gives us the correct correlations. Now, the other
I kind of can agree on the motivation on that, but maybe a very quick argument on why those systems are equivalent, because I could imagine if I were to stretch the spring, it would basically become a wire that's like slightly twisted, which would look very different from this. And of course, in your experiment, you don't stretch it a lot, but you do stretch it a little. So I'm interested in, well, how well it compares.
Okay, so the other approximation is the Biot-Savart approximation. And both of these approximations work if the radius is very big with respect to the distance between two coils.
Yes, so the solenoid approximation.
Yes, basically. Because if the spring is very stretched out, then you can imagine the coils don't really work that well. And if the spring coils are very distant from each other, then the Biot-Savart approximation of the infinite wire doesn't hold because...
okay, yeah, I think... we've maybe touched on this enough because I don't think it's too central to the problem statement. You mentioned a couple systems of differential equation. Can you maybe show the system that you got, or the equations that you got?
Okay, so you want to see the system again?
The system of differential equations that you got here.
Yes.
So for the first, I see that for the first things you have the driving term on one side, and there are 3 terms for the system.
Yes.
I'm not quite sure about whether the method you used to derive that is actually correct here. Because usually when one does the derivation of the LRC circuit, one starts from the capacitance. Did you do that? Or did you start from current?
Well, you can derive it in many ways, but
I think in this case it matters, because usually you start from inductance and then do a DDT to get to current, but that also creates another term, because inductivity is now no longer constant in time, so you get a term in this which is based on the derivative of the inductivity.
What do you exactly mean with start from the... You start from Faraday's law, basically?
So basically, usually how the LRC circuit is derived, and I think what you did is quite similar, is you start from basically like the state of charge of the capacitor, and that produces a voltage, and you have the voltages in the other systems. And then to actually get to the current, you do a derivative in time.
Yeah.
And usually that's not a problem, because there's almost just one quantity that's dependent on time, but for your case it's 2, and I'm missing that one.
Okay, yeah. So I actually said a remark about this. If the inductance changes over time, you add those 2 derivatives.
Okay.
Those 2 terms that account for that. So this is a standard equation for the RLC. And this is
This is what I was interested in.
Okay,
and I'm glad that you actually have it, because that makes it easier for us to discuss on that, I think. Did you try to solve that numerically?
We tried, but it's very difficult to solve it. I think it is possible, but you would need to introduce some approximations to solve it, I think.
Okay, then if the simulation didn't work, then how do you, let's move on to maybe discuss resonance modes.
Yes.
Where did you probably get your intuition of resonance mode and your knowledge from the experiment? What can you tell me about the resonance modes? Are they sinusoidal or do they derivate in some form?
Okay, so this is a nonlinear system. So to say that they are sinusoidal with confidence is not so good, but we can see graphically that they can be well approximated by sinusoidals. Now, one thing I want to point out, if I can expand on this a little bit.
Yes, please do.
We modeled that system in another way, linearizing it. So basically we used an internal model approach where you write the linear system, and I'm not going to go through the derivation.
To be honest, there's already something that I'm not sure whether that holds, because you did an assumption there that the...
Thank you. You might be able to discuss this after.
Okay, but...
We have now time for some questions from the moderator. Starting now. Let's go. Please use a mic. And click on the button.
Oh, thank you. So can you show your first experimental setup, please?
Okay. Here?
Yes, please. So where is the camera for the tracking?
The what?
The camera for the tracking.
We had a camera here. We didn't show it.
Okay.
We just had a tripod with a camera filming the spring. We removed it to take the picture.
Okay, and like when you added like the very large capacitor, how did you include it in the circuit?
So as you can see, we have a breadboard here. So we just use the breadboard to wire up the circuit, and it was pretty straightforward.
Okay, thanks.
Do you have any other question?
Can you show back also the simplification you made for the RLC circuits, please?
The what?
The simplifications for the RLC circuits in the end.
The RLC, okay. You mean, which ones are you referring to?
Like you said that you only took into account the last mass, is that right?
Oh yeah, so this second equation only takes into account the last mass. The other model had every mass.
Okay, thank you. I'm going to stop you, so sorry. 1 minute preparation time for the moderator. Yes, 1 minute added to your time. One minute left for the preparation of the moderator. Thirty seconds.
report about the solenoid resonance. So the statement of the subject has been well shown. It consists of an helicoidal spring hanging vertically, and we try to couple the mechanical system with the electrical system and study the different types of resonance and energy transfers between the different systems. The presentation that has been made presented several points. First, they made a setup with a power supply, wave function generator, a spring, and they used video tracking to study the mechanical system. They made a theoretical overview of the system by making some models, in particular the Biot-Savart for the infinite wire model, and they used Lorentz law in a simplified version for the force term. Thus, they had a theoretical model for the force in the spring. They added a model for the spring as a chained oscillator. They made some numerical equations, simulations, and compared it with the experiment. Then they tried to insert it in an RLC circuit, first by making a model to try and understand how the different terms were the different coupling terms appeared and how the different systems were coupled. There were some theory simplifications. They used a setup with a superconductor and then studied qualitatively the resonance conditions and the energetic aspects. So the discussion had raised many points. Some of them are fully reviewed, of which the approximation of the coil linked by spring and the way this approximation is sometimes correct, sometimes not, and the limitation of this approximation was clearly stated. There was clarification on the coupling term in the RLC equation, and the electric equation. There were an explanation on the numerical approach to the RLC equation and the difficulties of this numerical approach, and small discussions about the resonance mode. However, some points were not fully discussed, in particular the limit cases for the different approximations. They were mentioned but not discussed completely. The optimization of the spring in order to achieve this coupling was raised by the opponent but not fully discussed yet. The energy transfers were not completely explained neither, and the uncertainty in qualitative comparison were a bit lacking in the discussion. Thus, I would like to raise some discussion points, and first, the other way to make the mechanical system and the electrical frequency match, because this was your main problem, and this could be a great discussion about how we could improve this problem. So what do you think you could do about that?
Okay, so I think the best way to increase, we've established that we cannot increase the capacitance because we don't get any interesting situation that way. The only way you can do it is by increasing the inductance. Now, how you do that is you can do that with a ferromagnet inside of the coils, inside of the spring. However, the problem with that is that the magnetic fields created by the spring are extremely small. So you need a ferromagnet, if I can draw.
Yeah.
Okay, I'm sorry.
Yeah, I think it's quite clear. What you're saying is that you put a soft material inside.
Yeah, a very soft material.
Yeah, that's what
I think that's a nice idea. However, I would propose something differently.
Yeah.
Because one of the reasons why we can't make our coils very high in activity is because we only have one layer of wire. Of course, one could try to maybe have multiple layers of wire, but that would make the mechanical motion extremely complicated, so I would not propose this. But the system states LRC circuit. It doesn't state that there can't be multiple inactivities in the circuit, so I think it's good to put another inactivity in series that one could use, that one could optimize using the ferromagnetic coil, for example, and also put multiple windings around each other so that you get really high inductivity, and I think this would allow you to bring the frequency down and also bring your damping down.
Thank you. Okay, so if I resume the thing, you both have an approach on the electrical system, but do you think you can make an approach to, instead of lowering one frequency, maybe higher the other? Actually, how would you do this? Well, can you think about it?
This is actually basically impossible because you cannot physically bring the resonant condition for the spring to the order of 50 kilohertz.
Actually, I tend to disagree, because I think using your model one can actually find a possibility, because when you presented your spring, it was mass with a spring between each other, and that model is a very simplistic model to describe solid-state physics. So it's a 1D linear atomic chain, and that chain has multiple modes of excitation. So, for example, the mass and the masses of the spring can also oscillate against each other, and the frequency of those modes would be much higher than the mode where the whole spring oscillates in phase. So I think by using those high harmonics, you could actually get really high mechanical frequencies.
Thank you. I think we will move a bit, because the time is up, we can move on the energy qualitative study, because this is a part of the subject and we didn't discuss it yet. So what do you think, how do you think you could improve your modelization in order to more take into account or more explain how the different energy transfer works?
Okay, so what I wanted to explain before that I didn't have the time to do is from a qualitative point of view, if you first give the current that isn't resonant with the circuit, then the current goes up, thus the length of the spring on average goes down, and the inductance goes up. Now, this causes a change in the resonant frequency, therefore we're no longer in resonance, and the current thus goes down.
I believe there is actually a quite simple model, and please tell me if you agree, to model the case that you observed in the experiment, where your electrical frequency is many orders of magnitude higher than the mechanical one, which is that because the force is always attractive no matter the current points, we get a net positive force, and this is kind of averaged out by the inertia of the mass, so that you can treat that like the mechanical oscillator with a DC current, I believe.
So what do you exactly mean?
So I think the system that you have in your experiment, whether you have a mechanical oscillator and you have a very high frequency electrical oscillation, is kind of the same as the mechanical oscillator with a DC current that was 1/√2 times the amplitude of your high frequency oscillation, I believe.
Okay, so just one thing I want to touch on is that you cannot compare atoms with a macroscopic spring, because you can have, it's very difficult for you to have a very high frequency and the spring oscillating significantly, because the masses involved are way bigger, therefore the inertia of the spring cannot follow that frequency.
I think you would have actually observed.
Sorry to interrupt, but I think we're just a bit shifting from the main subject. The idea is to study the energy transfer. So maybe the main idea is what are the different energy forms in the system and how do they transfer from one system to the other. Maybe you can explain this a little bit.
So the energy contained in the spring is both a kinetic energy due to the motion of the spring and a potential energy due to the spring itself. So an interesting thing we can say for if the systems are decoupled is that by providing a small frequency, frequency from the generator, you would need more power to actually run the circuit, because you would need the power to actually move the spring other than the power that is contained in the circuit.
I think that kind of answers like the first thing, that the current will transfer energy into the mechanical system because it poses an attractive force. And if the phase of that is correct, it will enlarge the amplitude of the motion of the mechanical system. So I think that one is quite intuitive. What's, I think, less intuitive is how a current can be induced into the electrical system. Because induction normally needs magnetic fields from, like, for example, a moving static magnet. But if, well, there is no such thing here. And what I believe happens for that is, for example, that the magnetic field is created when the inductivity is high, so it doesn't need as much current to create the magnetic field. Then the coil is enlarged so that the inductivity goes down. And when the magnetic field kind of is destroyed, as is usually the case in the LRC circuit, that happens periodically, a larger current will be induced because now the inductivity is less, and that's how we can drive it.
And how do you agree with this interpretation of decoupling between the two systems?
Do you agree that this is similar to the qualitative analysis that I give? Because
to be honest, I think you talked about power supplies and power sources, and I more talked about the ways that in the LRC circuit the energy
So you concentrate on the actually energy exchange, while I concentrate on just a more high end.
I think we're a bit on a dead point there.
The
You can move on to the next point, the limits of your models.
Can we actually go back to a really important point, which
Okay,
please.
If I can you had 5 minutes for this.
Okay.
You talked about the limits and the way limits appears, but you didn't explain how the limits manifest themselves inside the models or inside the experimental data you gathered. And did you have any information about how the limits of your model was present in your data? Can you explain this?
Okay, so what can we say? The big difference, I feel like, is that we are using approximations here that yield us this formula. Now, if you were to use a more precise calculation, I think you would have a similar formula just with a different constant term. So now we see that the force is proportional to the current squared. A more precise approach would have yielded a different constant, multiplicative constant.
Okay.
But from our system, I think these approximations hold pretty well, and this is also confirmed by the experimental results.
Okay, so what do you think about this?
I think the more precise equations that you mentioned is that the force is proportional to, as your model predicts, the current. But there's also the length of the spring here. To be honest, I don't quite remember whether there's a correct term at the bottom. But I think this is the one that would be. I mean, maybe you get something similar out of
those
this.
Z terms are the positions of the coils. So the force goes down if the coils are more distant. So I think the approximations.
I think that's really interesting for how the modes look, what you just said. Because the force goes down when the coils are more distant. So I think now we can kind of combine some topics that we talked about, which is how the resonance modes look and the high frequency limit. And I don't know how much you agree on the DC case, but maybe we can get some idea on how the modes would look for the DC case.
I'm really sorry to interrupt, but I think we just finished our discussion and we'll have to just
we're done
resume
here. Thank you very much.
Okay,
Let's have
so
some conclusion from the reporter.
This was a challenging problem, especially from an experimental point of view. I think we managed to solve the problem pretty well, although the last part was incomplete, but we did manage to give the conditions that the system needs to satisfy for that to happen. And I think we could have talked a little bit more about the resonant frequencies of the circuit, because we didn't really discuss that aspect. That would have been very interesting. But overall, I'm happy with the discussion, and it was very fun to solve this problem. So I thank you for your attention.
Now time for the jury's questions. Anastasia?
Okay. Does it work? Thank you. So when you're measuring the frequency response for the system, is it like this swiping? It's called swiping, as if the wave generation is doing, right? So you can like set, okay, I want to scan from this number of hertz to that number of hertz, and you get the measurement. Did I get it right?
Yeah. So the frequency response, we fix the amplitude and vary the frequencies of delta and measure the amplitude of the oscillation of the current.
So you said that your second resonance is like discrepancy between the frequency for the second resonance for the experiment and simulation is motivated by the fact that your mass and elasticity are fitting parameters, as I got. But why it didn't impact the first resonance but only second one? Why didn't it impact the first resonance but impacted the second resonance?
Actually, both resonance are a bit shifted.
Is it? Okay, show me again.
Yeah. So,
okay. May I comment on one of the plots? I believe may I comment?
Let the reporter finish.
The resonances are in the simulation are a bit shifted forward.
Okay.
So,
so I think this is also something.
Short comment.
Okay, I think there would have been more peaks if you continued this experiment for a lot longer in frequency space.
Okay, thank you.
Christoph?
If I understand correctly, part of the three-way discussion, Christian wanted to say something about the prospect of increasing the mechanical frequency so that that experiment would be doable, something that was actually ignored by the moderator. So I would like you to have your chance about that.
Okay, this is actually just what I was kind of hinting at. I believe that there is higher frequency mechanical oscillations that are possible, which would have showed up in this measurement had the frequency been swept to, I don't know, like in an order of magnitude, I would guess maybe 50 hertz or 100 hertz. Maybe there's even resonance frequencies at higher points because the reporter modeled the system with a linear atomic chain, which I think is it's a nice ansatz, especially if the mass attached to the spring is quite small compared to the mass of the spring. And I think in this case, the number of springs is kind of the number of turns of the spring is might be the number of resonance modes in that system. And of course, there's also resonance modes that are where, for example, those are the masses, so in your case, the coils, and I believe that there is a high frequency case where the motion is like this. And the frequency of this kind of motion, I think, could be orders of magnitude higher than your ground mode, and it would have been maybe suitable for a coupling experiment.
Okay, so if I can add to that.
Very short, if it's...
We actually modeled with the MATLAB simulation what would happen if the frequency would increase. Now, what happens is that there are more resonant frequencies, however, they decrease. And basically, you cannot see it macroscopically. In fact, experimentally, after 3 hertz, we did manage to find the resonant frequencies, but they were so small that they were basically insignificant, and we couldn't even measure them accurately enough.
Okay, Oman?
Okay, thank you so much. As I understand, what part of the problem is related with how the current impact the spring. So, could you comment something on that? What's happening with the natural frequencies of the system when you change the current? Yeah, part of the discussion was related with the mechanical part of the system, but until this point, nothing is common about that, moving or changing the current. Could you comment on that, all of them?
Okay, so we have 2 things that can happen. We can change the frequency and get different peaks. By changing the current, yeah.
How it changed the frequencies?
So by changing the current, we get that the resonance, the oscillation goes up, the oscillations goes up, and it goes with the current squared. So this is the first graph that we showed here. So this is fixing the current, fixing the frequency and varying the current. So you see that the trend is parabolic. While as fixing the current amplitude and varying the frequency, we get different modes. And each of these modes are associated with nodes. So they are, but this is another topic to discuss, actually.
Okay, Aurelio?
Okay, and maybe can you repeat the question again, because I was so focused on the discussion, I forgot part of it.
Yes, it was related with the action or the behavior of the frequencies, the natural frequencies of the system when you change the current in the system.
Okay, I think this is too much, unless you can answer yes or no.
I don't expect a change in frequency if one just varies the current.
Okay, Aurelio?
Yeah. Thank you, the 3 of you. And my question is also for the 3 of you, but try to keep it brief. Keep it brief. Just, let's focus then in the reporter. Could you, in your own words, explain to me what is the energy transfer, which I think is one of the main points of the problem. When you are doing the thing with the RLC system with the mechanical one.
Fourier transform?
No, I mean the coupling. So how is going to be the energy transfer from one to the other? Explain it with your hands.
Okay, so the energy transfers. So we can have 2 directions for, say. The first direction is for the electrical energy to be transferred into mechanical energy. And this goes, basically uses the current as its transfer motion. So we've seen that with a current, the spring moves. Therefore, parts of the electrical energy gets transferred into the motion of the spring. This is why also you need a bigger power supply in order to actually study that system. The other part is actually way more difficult to analyze, and we touched on this during the discussion, because it's kind of ambiguous. So
I don't think it is.
May
if I'm allowed to
add something, maybe? Or
are we allowed to comment?
Very.
Yeah. So I think to answer briefly, the way the electrical and energy is transferred to the mechanical is through the work of the Roentgen's forces, and the way the energy is transferred from the mechanical system to the electrical system is from the induction tension from the magnetic flux varying in each coil.
Yeah, if I can just...
I'm sorry, I wanted to also comment on that in the interest of time, I think. So I think I've kind of touched on
I
that.
think we move on to next question, sorry. Unless it's really...
Thank you. I think the coupling would be much larger if the mass hanging to the spring was magnetic. So question to the opponent, is there something in the wording that does not allow this?
Okay, that's kind of a difficult question. I've never thought about that case. I mean, I think the phenomenon they're describing would happen because there would be inductivity in the system. I mean, at that point, it's no longer just an LRC circuit. I'm not sure whether that would really apply to like stricter definitions of the problem statement, but I think that would have very interesting, it would allow for more strong coupling. Oh, yeah.
Okay. Nino?
So we didn't really get to discuss the spring optimization that much. So this is a really brief question for the reporter. Since you're passing 5 amps through your spring, do you have any issues with it overheating?
Heating?
Yeah, with the spring overheating.
Okay, so we didn't touch about the material used, but we chose aluminum because it has a very low resistance. Therefore, we could supply it with a high current and with a relative low heating effect. Also, the spring has a very high surface area, so this helps in conducting the heat out.
Okay. Julia?
Thank you. I have a question for all of you, starting from the moderator, opponent, and reporter. Could you shortly say what limits the energy transfer efficiency from the mechanical to electrical modes? What limit efficiency of the energy transfer from mechanical to electrical mode?
From mechanical to electrical, I think the main limit comes from the tuning between the two frequencies. Thus, it depends really on the difference between the resonance frequency, the fundamental resonance frequency of the mechanical and the fundamental resonance frequency of the electrical system.
So the way I imagine the transfer of energy from the electrical to the mechanical system, I kind of try to explain that during the discussion, is that the magnetic field is created when the inductivity is large, then destroyed when the inductivity is less large, so that there's a larger current induced, in my opinion. And I think the efficiency of that, I think, should be comparable to, for example, electric alternators, because there's also an electromagnet creating the magnetic field that then induces a voltage in a coil. So I think in some way it's similar to that system, I would imagine.
The reporter, please, short answer.
So the efficiency is a pretty hard problem to solve, I feel like. You see, I think what we would actually see, just as a hypothesis, is for the mechanical oscillations to go up and then down. So basically a sinusoidal modulated by sinusoidal. So part of the mechanical frequency would dissipate, but if you don't take into account dissipations due to the air.
I'm sorry, please, shorter, please.
Okay.
Short answer.
maybe we could have a higher efficiency like this. But
Thank you. And now, Frederik?
Yes, I have a small didactic problem to the reporter. You had this boat diagram which spanned, what was it, 5 orders of magnitude. Could you please explain the significance of that to someone who rarely sets foot in a laboratory?
okay. So, would you like to know why this doesn't work, or what a boat diagram?
That you have this flat plateau across.
Okay, so a boat diagram, basically, given a certain input, which is the voltage supplied by the power by the generator, it gives out relative to each frequency the output. Okay, so the amplitude of the output, which in this case is the current. So what this means basically is that if we have low frequencies, what happens basically is that the capacitor acts as an open circuit. So there's low current basically. In intermediate frequencies, the capacitance and the inductance acts like a resistance, more or less. Therefore, we have a resistive circuit. And in the higher ends of the frequencies, the inductance acts itself as an open circuit, so the current goes down. Now, having this big plateau means that the current gain in the frequencies that are reasonable, so 1 hertz, is constant. So we're kind of studying the problem we had before, just with a different boat diagram, but this doesn't change anything in the end.
Okay.
This is why it's not significant.
Christos?
Okay, so I would like to continue this question and also the question about the spring optimization with a small but rather interesting mind experiment. Could you have a spring that operates in the kilohertz region?
No, I don't think that would be possible. Or for you to have that, you would need masses that are extremely small. So for atoms, that is possible. Atoms are actually, we can model them in that way. But for macroscopic masses, it's very difficult, basically impossible, I would say. Also because the resonant frequencies depend on the elastic constants and the mass. And these two values are related, are not interdependent. So
can we bend on this? Just
I think we don't have much.
Very short, extremely short.
Go.
Yeah, it is possible with carbon fiber. This is my answer. Because it's very light and extremely dense, and if you make the compilation, you have 10 kilohertz as a resonance frequency.
I believe if one's allowed to use non-conductive materials, especially non-metals, it's easy to do a spring that's in the kilohertz range. But if one wants to use the metals from the problem statement that we used, I think it's possible to make it much higher by making the spring constant very stiff. But kilohertz range, I'm not sure. Maybe only if whether the ground mode can reach that.
Thank you, Christian.
Thank you.
Now it's time for the jury to decide their grades. Now it's time. We won't have any feedback. I encourage the juries to seek out the participants if they want to give feedback. But we will move on to a lunch break now, where before you leave,
please
be
keep seated. We have some announcements.
Yes. So we will have to be here back at 2:30. So it will be a rather short lunch break. For those, you need your badges to get lunch. And for those of you who don't have your badges, we have temporary ones outside that will work on both exits. Jean?
Yes, we will ask the jury members to give us your scoring sheets. And finally, our beloved LOC president has something to say.
Yeah, thanks, Guy. So, people who do not have their badge, you will not get food. Because it's Saturday, it's like this. So people who do not have a badge, we have printed this replacement badge. Helpers are waiting for you to come if you don't have one, okay? Really important. Now, the way to the cafeteria, to the Mensa, is different, okay? You'll have to go through the B floor, okay? B floor, not outside. We have people waiting out, okay? And the easiest way to go to the B floor is you simply go straight out on the other side of the building on the F floor, okay? And then on the right, you'll get a huge elevator, and you simply go down to the B floor, okay? You can also go down with the stairs to the B floor, okay? But just make sure that you do not use the regular way. And if you're lost, write on Discord, there will be helpers along the way to help you, okay? Thanks a lot. Oh, the time, okay? So the closing ceremony is supposed to start at 2:30, okay? This will probably not happen, okay? But after 2:30 at the Mensa, we'll try to tell you to come, okay? So we should maybe do 2:40 or something like this, okay? Please try to make it quick. Thank you.
Okay. I will give the sheets.
Yeah.
Okay, hello everyone. We're going to start the last part of the closing ceremony, so please take a seat. So welcome everyone. This is the last part of the closing ceremony. I guess you all know me by now, but for the people who are with us on YouTube, my name is Mathieu, and I'm representing the LOC today to give a few words. I have to say, what a ride, what a week. I just feel all the intensity slowly coming down and all the realizations about what has happened. And if you remember at the start of the tournament in the opening ceremony, I asked you to think about what the IPT could look like for you in one simple concept. And I had proposed you this idea of the IPT baby. I don't know if you really bought it, to be honest, but I certainly like it. It looks cute. And I've been thinking a bit during this week, and I think I have changed my mind about what the IPT looks like to me right now. So this was him, and now this is him now. This is you. I think you are the IPT. All of the work that you've done, all of the presentation that you've made, all of the feedback that you've gotten from the jurors, all of the friends that you've made, all of that has been infused in you. And all collectively, we are the IPT and we represent it. I want to single out a few people from this big group. Well, not yet. We have some cool pictures we took. We're gonna give it for you, but I have a few sneak preview, and I think this captures really well some of the aspects that you got to do this week. So of course there were the physics fights, which were super stressful and intense, but I'm sure that you really enjoy them, and we saw today the presentations, and it was absolutely amazing what you guys have done. You got all of this feedback from the jurors. I know it's always a bit of a, some questions about how the jurors grade and stuff like that, but it's good. It keeps your blood pumping, a lot of, angriness and a bit of drama. There was also all these excursions. You could discover Zurich, not only just ETH, but also around. Tonight we're going to have this barbecue in the Hunkerberg, so there's a magnificent view. If you walk a bit, you can really see all the mountains and the lake. We've been to CERN PSI. We've been to different places where you can really enjoy the city. And most importantly, you haven't been there alone. You've been here with all of your friends that you've made, all of the other people that also suffered with you and that you bonded together. And there's this really cool picture, I think, of the creation team which jammed together. There's going to be some music tonight, so I encourage you to show us your skills. Now, this would not have been possible without all these people that helped us, and I already apologize in advance because there's way more people that helped us than the people on the sides. But the 5 helpers that helped us during the week, Alisa, who's unfortunately not here today, Florian, Kaspar, Moritz, Alejandro, you've been doing all of the work in the shadows to make all of the details work, and there were many, many, many details. But if you guys had the impression that things went okay, it was more or less smooth, that was thanks to them and all their hard work. So I think we can all thank them. I actually want to say, the 4 first people here were part of the IPT last year, and so this gives you a little idea of what impact the IPT had on them to do all this work for us this week. Another few people that came and helped me, I want to thank you, Jeanne, Katia, Quentin, and Arnaud. You've been really a great help, not just practically speaking, but also for the emotional support and talking, and I love all your feedback and discussions we had, so thank a lot. Now, it has been a very long journey for all of us in the LOC. And I want to spend a bit of time thanking everybody here, because that week was really this intense result of all this work that we started last year. And so I want to start with Alberto. Where are you? Ah, there, thanks. We've known each other almost for a decade, actually counted. Feel old. And we actually participated in IPT in 2018 together. And if it wasn't for you for proposing this kind of crazy plan of organizing the IPT here, I wouldn't have done it. So thanks for being a visionary and seeing how great it was going to be. We have Thomas on the right, who's unfortunately not with us here. Thomas was an amazing help because he sorted a lot of problems that we had, and he knew exactly how to solve them. Before and then even during the week, we had a lot of very tense moments about the organization, and he really handled that amazingly. And I really feel almost sorry for him for all the urgent things that we put him in, all the problems that we came up with, but he handled that like a pro. So I think we should really thank him a lot. And last, but certainly not least, Andreas. Are you here, Andreas? Back in May of last year, you had two kind of naive and crazy PhD students come into your office and propose you this crazy plan about organizing the IPT here at ETH. And if you didn't believe in us, if you didn't say, yes, let's do this together, if you didn't have this dream we had together, this could not have been possible. And I really mean that, every single word of that. You've been doing all this work with all your influence and all your passion, and you really guided us into making this competition something that was wonderful and worked out. I could really feel all your passion and all your excitement about the competition. And you've been a great inspiration for us on how to lead, how to enjoy the process, and how to make something magnificent as the IPT. So thanks a lot from the bottom of my heart, Andreas. Some more people helped. Not really people, actually don't have faces. We had a bunch of sponsors. And of course, without the sponsors, this would not have been possible. We have had an amazing IPT. We've tried to really make it a great experience for you with some coffee breaks and beers and visits. And so these are all the companies, institutions that helped us. So I'm quickly going to go through them. First of all, of course, ETH, I already said it at the start, they've been providing us not only with some substantial funding and money, but also with the infrastructure, the people, the organization, all the people that helped us for the small things, the big things. I really want to thank them a lot because, again, this is how everything works in the end. Then we had the city of Zurich. They were responsible for the city tours, for those of you who went. They also gave us some of the stuff for the goodie bags, and they've been really nice and really trying to promote the city. We have Swiss Life, who contributed also financially, and the Swiss Physical Society, who represents physics at the national level. And actually, the past few days, we've had someone who represents them who's been learning about the IPT to try to talk about it more and to spread it more in Switzerland. I don't know if Martina, you're here. Yes, I hoped you enjoyed it as much as we had, and that you'll manage to spread that enjoyment outside of this hall. Thanks for coming. We also had our sister school help us, which is really cool. I actually did my bachelor's of physics at EPFL. I participated in IPT with the EPFL name. And I think we have Jean-Marie and Jean-Philippe somewhere. Yes. Thanks for helping us a lot. I think we've had a great connection with EPFL, and we should keep doing that. We had our national selection, and it's always a pleasure to have you around. And thanks for helping us also with the tournament. We've had SwissMap, who care more about the mathematical parts of physics, and I'm sure they will not be disappointed because there were a lot of great theories that you came up with. So they've helped, as well as the Paul Scherrer Institute, PSI, that some of you visited. They've also helped. And finally, we had actually a few foundations that generously supported us. And these foundations really help organizations and events that have this goal of promoting science, making young researchers learn about how to do great work and become better researchers. And so they've all contributed to that because they believed in us, and I think they will not be disappointed because you guys did amazing work. Now, if this were a YouTube video, this is the point where I would say, I would like to thank our sponsor, Brilliant. You guys love physics, working on hard problems, and Brilliant has plenty of them where you can work them through and work on your critical skills. So go to the brilliant.org/IPT to get a 20% discount on the subscription. Now, of course, this is not a YouTube video, so I'm not going to say that. Wolfram, like last year, also proposed us to give you licenses for 1 year. And when I told them about that, if they want to sponsor us, they told us, well, we can give you a license for people that are in the semifinals or the finals, but they have already done the IPT, they have already done the work. And they told us, well, you know what? You should give it to people that are also going to use them for next year. So if you're interested and you want a mathematical license, you can come to me and they can give it to you. And team leaders or IOCs who are going to prepare it for next year, you can also request a license so that the future participants of the 2025 edition can also have access to it. So that was it for the more, sponsor financial part. I want to remind you that IPT is actually not over. This is the closing ceremony, but we're still staying together for a bit more. We're going to have our barbecue this evening, and this is kind of the last occasion where we're all going to be together without the stress of the physics fight, without all the intensity, and we can finally enjoy a well-deserved rest and beer and sausage, and there's also vegetarian options, so don't worry about it. And it's going to be at 7 this evening in Hunkerberg. We're going to show you exactly where. So please all come. This is really the last moment where we're all going to be together and try to meet people and talk because this is the last opportunity. I'm going to be there. I'm certainly looking forward to talking to you. I want to say a final few words about how it's been for me this week. And it's been absolutely amazing experience. As I told you, the reason we did this with the LOC is that we really believe in what the IPT can bring to all the students. And I've been savoring every single moment of this whole week, no matter how intense it was. And I'm sure it was the case for the other LOC. And that was the reward. That was the reward of all the work that we did. And again, I think it's captured really well in this picture. I made you a promise in the opening ceremony. And that promise was that by the end of the week, by the end of the competition, basically today, and then in the next few days, weeks, months, maybe even years, you will look back at the IPT and you will have all these fond memories of all the friends you've met, all of the presentations you've had, all the crazy judges that didn't understand you, and all of the hard work that you had to do to come to this point. And I think there's a big transformative element in that, and it certainly has transformed me. All of this year, all of this week, I think it has made me a better person, a more joyful and excited person, and it really also reinvigorated my love for physics. And so I hope it would also be the case for you. And I invite you to actually, once all of the intense moments slows down and you're all going to go back home, reflect a bit about how the IPT actually changed you, how it transformed you, how you're going to do, maybe approach a problem in a different way. Maybe you're going to present in a more educational way. Maybe if you go to Italy, you contact the Italian team and you get a pizza. Maybe you go to Germany and they get you drunk with beer. And if you come to Zurich, certainly write to me and we'll also talk about the good old times. And so I want to end this by really thanking you all from the bottom of my heart. It's been truly amazing. If I could, I would hug you all at the same time. But I'm going to try to do that individually at the barbecue, so we are going to see you there. Thanks a lot. And it is now my great pleasure to introduce Anastasia from the IPT presidency.
Thanks, everyone. Thanks, Mathieu. It was a great speech as usual. And eventually, while I'm speaking some nonsense, my mic will start working. But maybe not.
It's fine. Do you have some slides?
Yes.
In your computer? Ah, okay.
So it seems working. Hi, everyone, again. I think it's a boring slide. We'll go for next one, because the Mathieu definitely gives and says better and more complicated words than I can do. But I'm super grateful to my team, which is obviously less organized than the LOC, but fully driven of the passion of providing physics and providing great educational experience to all of you. And seeing your excitement and seeing how much you are enjoying the discussions and how much you are enjoying meeting other people, it's the greatest pleasure we can have. So you pretty much saw the slide, but can you imagine, for example, that Akash had to deal with the streams, Instagram lives, that's what I mean for streams, did the announcing for semifinalists for you, and also organized the IPT conference. Can you imagine how much this is multitasking when we are doing the IPT? Or can you imagine that Christos been doing all these fancy cat videos? Did you like them? And every night when we are super tired, he's like was very dedicated to go to edit all the inputs, to double check with the schedule so you all enjoy and make a lot of use of that. Or Vova was also compiling the captain's fights for us for also quite a late time, including today. So you didn't see the last wordings which we planned for the captain's fight today, but hopefully you enjoyed it as much as we enjoyed coming up with the ideas. Did you? I'm pretty much going random, but for example, Maya just joined us quite recently, but she's already gaining a lot of IPT experience and been chairing throughout all 4 selective fights. You actually cannot imagine how much is exhaustive to chair captain fight or overall physics fight, because you have to take control of the room, you have to take control of the time, you have to listen what you're saying, so I'm not saying something which we have to interfere with, and also to coordinate with other 6 rooms which we have on site, so everything is done smoothly and in a more or less synchronized time. Can we, on the example of Maya, think of our chairs? I'm tired, whom I didn't mention. Okay. Then we have Kirilo, who is mentioned here like a treasurer, but actually he is a core driving force of the IT infrastructure we have. So did you see the IPT Connect and how much is different from the user perspective this year and last year? And he invested a lot of his time to actually make it working. And it's even more complicated behind the curtain. Like when we have to insert grades in the IPT Connect, it's now absolutely smoother experience than it was last year. And hopefully we did fewer mistakes this year, which is actually very enjoyable for us as an Execom. Shall we congratulate his achievement for that? And I think obviously the most multitasking among here was Alberto, who had to deal with the secretary duties, which include a lot of internal IPT businesses, and do it together with LOC vice president duties, which is involves of knowing where we're going, knowing the information about the room booking, and these sort of things. Really, my personal impression is that IPT people are the most, IPT organizers, it's a great experience which just changes us and learns us to communicate things, to deliver things, to make things on time. And it's what we learn here, and it's why we find this experience valuable for us as organizing team. So let's congratulate Alberto as well and all my team here.
I take this opportunity also to share our IPT community thanks to our first IPT president who passed away last autumn. The Professor Oleg Skelnik from the Taras Shevchenko Kiev National University has been elected as IPT president in 2011, and suddenly, after a long and complicated disease, he passed away. I think in such situations, it's appropriate to do some personal anecdotes, and my story with Professor Kelnik was that in 2011, for the Ukrainian tournament, we had an appendicitis crisis for one of the team members during the final, during the opponent preparation time. And it had to be emergency, and some people came. And the emergency car stuck actually other side of the campus, something like half kilometer away. And the Professor Kelnik was the one person who actually took care of everything to deliver the emergency team from some unknown destination to us so we can carry our team member to the hospital. And it's this attitude of making things sorted because it's a critical moment, and when you need to stay focused and deliver your objectives is kind of attitude I really appreciate in people around, especially in Professor Kelnik. So I hope you can join me for condolences and for our gratitude for his contribution to the first year of IPTs when it was just starting, but we are here because he was in the first years of this movement, of this event. And thanks to all of you for this great IPT week. I didn't have the group photo, sadly, which I could have requested, but I just decided I'll go the easy way and find some photo which represents the fun community of us a week ago, but this week feels like an ages now. So a week ago, we were less experienced, we knew less physics, we had less excitement in our minds, but we still were as much in love with physics as we are today, and we're gonna stay in love with physics throughout all our life. And it is because this event is gathering together very enthusiastic, very hardworking, and very talented people. So thank you for being, it's my bad, thank you for being a part of this week today, and thank you for shaping this event. So this is my address, and at this moment I want to actually let you know that we had Mayuri as an IPS president on site throughout yesterday and today, and the EPS, is European Physical Society, is an umbrella organization in Europe which is taking care of promotion on physics for all the career stages, for education and research. And Mayuri also has her address to give to you on behalf of the EPS. Please join.
Okay, good afternoon to everyone. So my name is Mary Sakellariadou. I'm Professor of Theoretical Physics in King's College, London, and I'm the President of the European Physical Society. So on behalf of all of us at the EPS, I would like to congratulate you. I was here just yesterday and today, but I'm impressed from your passion, from your energy, from your skills, from your enthusiasm. So if for 1 minute I just put the hat of a university professor that I am as well, I would like to thank you. Because for us, it's fantastically rewarding to know that the next generation of physicists, the people that we have been teaching, are just people like you. So thank you very much for your enthusiasm, for your work, for your skills, for your passion. It's just wonderful to see that. And I would like to congratulate anyone, all of you, anyone individually, the people who compete, the people who train you, and he went with you the whole year in order to be at the position that you are today, the organizers. So this is an action that by all means has to continue, and if anything, just to be expanded. So having said that, I would like to tell you a few things about what is the European Physical Society, and try to see why probably if you are not members, it could have been a good idea, or it can be a good idea to join us. So we are a federation of European physicists, and we represent all European physicists, no matter which country they come, no matter what field they are. So this society, the European Physical Society, was founded in 1968 in Geneva. Right now, we have 42 national member societies, which means, let's say, the member Physical Society of Italy, of France, of Greece, of Poland, whatever. So that represents something like 130,000 people. We have 40 associate members, which can be research institutions, for instance, CERN, CNRS, INFN, and so on. Universities, also industry, and we have about 3,500 individual members. The headquarters are in France, in Mulhouse. So if you want to see what is the mission of the EPS, then I'm going to read what we have in our webpage. Contribute to and promote the advancement of physics in Europe and in neighboring countries by all suitable, let me see here, means, and in particular by providing a forum for the discussion of subjects of common interest and by providing means whereby action can be taken on those matters which appear desirable to handle on the international level. So the structure of EPS, we have 12 EPS divisions representing all the range of physics topics. So we have atomic, molecular, and optical physics, condensed matter, physics education, environmental physics, gravitational physics, high energy and particle physics, nuclear physics, physics in life sciences, plasma physics, quantum electronics and optics, European solar physics, statistics, and nonlinear physics. And in addition, we have 6 groups: accelerator, computational physics, energy, history of physics, physics for development, technology, and innovation. So these groups are independent, but of course under the umbrella of EPS. So they have their own board, which is elected every, I think, 4 years. They have their conferences that they can do. They can somehow organize an event with a national physical society, and they have their awards, their prizes, and they try to stimulate work among collaboration among physicists coming from different parts of Europe. So what we do, we promote physics, we facilitate scientific exchange, conferences and publications, European scientific policies, so we have an office in Brussels to try to somehow encourage financial support in physics and as well somehow to have a role for the scientific policy in Europe. We try as well to help for an integration. We live in a world that is a tremendous fragmentation and division. So what we try to do is to put scientists together, to work together for a dream, for a cause, for something scientific. And in addition, to help countries in eastern part of Europe or southern part, central part of Europe, where somehow they need more support for scientific kind of events. So we have some kind of regional activity as well to help local communities in physics. And of course, we have a cooperation with other societies, either within Europe or, for instance, with our colleagues in the US. So something which can be particularly interesting for you is the EPS Young Minds section. This was started in 2010 as a platform for students at the bachelor, at the master level, or PhD students, or postdocs in order to form a network. So the objective is to develop future researchers in physics, all of you, promote physics among the broad public, so there are quite various outreach activities that take place, connect young scientists in Europe, and the approach is to create an infrastructure for young physicists to emerge and get involved, support self-organized local sections, and also, this doesn't work very well, encourage interaction between sections. So here you can see the network. There are some stars that you can see all the Young Minds sections which exist in Europe. You can see the web link that you can go and see which are the sections if they exist in your country. You can easily form a new section if you want. You just need to bring together people from the 3 categories, bachelor and master, PhD, and postdoctoral level. And then you can form a section, and then you can collaborate with sections of your country or sections of another kind of Young Minds section within Europe. So the benefits which you have, funding opportunities. So you can have a grant for some scientific activity or a grant which is given through EPS in order to attend the conference. There are meetings which are organized from these young mind sections through the whole Europe. They have a particular section in the Europhysics news where they can advertise their activities and they can somehow put together the network of all the students. And then they can as well get financial support in order to attend particular conferences organized by divisions of EPS. So I would really encourage you to join them or somehow to be part of them, or I don't know, that's something that we can discuss, but for sure is something that is profitable because the whole idea is to create a network of early career physicists within Europe. So having said that, yeah, that's the things that I tried to say before. Having said that, I would like once again, on behalf of all my colleagues in EPS, of all the national societies which we represent, because at the end we are the voice of physicists within Europe, I would like to congratulate you all for your energy, for your enthusiasm, for the passion which you have, and is really very, very necessary. And I'm really impressed by the level of the presentations which I heard. It's really absolutely wonderful. So congratulations to all of you. You are all winners at the end.
Is it fine like that? Thanks. Yeah, thanks a lot, Mary, for coming here today. It's a great pleasure to have you, and so you could see the IPT experience. I actually do believe, talking to you a bit, that the EPS and the IPT do have a lot of core and common values, and so hopefully we can continue to work together in the future. I was afraid that I would have to do that, but one of your greatest qualities, Anastasia, is your humility. You're a very humble person. But today I'm not going to let you go with it. I want to thank you again from the bottom of my heart for all the work you've put in the IPT. I've said you were all the IPT, but then you would be the cornerstone of it. As the president, you've poured your heart and your soul in the organization for many years, and this year again was amazing. And without you, this whole thing would not have been possible. And I really feel like all of this passion, all this enthusiasm just percolates through all of the different levels, all the way down to you. So I think we should give a huge round of applause for Anastasia. All right, so with that, I think we can move on to the next stage of this closing ceremony. And that would be giving a few prizes away.
It's going to fall. So we have many presentations, as you can imagine, and we're preparing slides almost as organized as you do. So if I can have this laptop on the screen. So we have the individual awards, as you may be aware. So we reward the person who did the best report and earned the best grades from that, and they earned the best, did the best opposition, and did the best moderation. I think it was the biggest challenge this year. So I have a clicker, I'm even more equipped than I thought. And we're going to give them away now with me and Mathieu and take lovely photos on the stage with all your names there. So we have the best reporter this year is Pablo Margolo. Congratulations. This is your diploma. You can stay here on the stage, okay? And wait for other two people. Okay. Perfect. Yes, okay. I'm going to take many photos today. So if you think it's actually the final report, it wasn't. So my point is, it wasn't the final report. It's not our sneaky way to reveal you the results of the final. It's the grades we earned during the selective fights. Yes? Yes, okay. Maybe semifinals, I don't know. So, let's move on. Then we have the best opponent, and we actually have 2 people to congratulate with that. I need other things. Yes, yes. You. So now we have 3 people on the stage, but it doesn't mean we finished with the slide yet. But I have too many things in my hands. And it's all not your slides, and it's not your slides. Okay. So, Nikolai Christian Kondstad from the team Denmark for alcohol sound check. And Martin Brendan with US team with PVC semi-droplets. Let me have. And you may expect now that we're gonna reward the best moderator, and it's Arina Mironova from team IPT with Galton board. Let's take more photos. More photos. We should move. Taking too much space. Let's thank again our best players of IPT 2024. And then we're doing teams. Then we on the next slide.
All right. So now we're going to the team's rankings. And of course, you probably already know what some of the rankings might be. Still, I would ask you every time you see your name, calm down, okay? We're going to take a picture and we're going to give you the certificates. And then we move on to the next team, okay? So the first team that we want to congratulate today is Mexico. Thank you guys for coming all the way to Switzerland. If I'm not wrong, I think it's the first time we have Mexico in the IPT, and it's been an absolute pleasure to have you around. So thanks for coming.
We have secret storage for diplomas. Very real things. Who is team captain? Please. Okay. Thank you.
All right. Next team is Spain. I think it's been a long time we haven't had a Spanish team at the IPT, so it's great to have you guys back.
Who is team captain now? Very good.
All right. Next one is Poland from Krakow. Thanks a lot, guys. I know you came on pretty late notice, so it's great that you could come. And you did a great job. Thanks.
Thanks for coming. Let me pass it to girls. Yeah, appreciate girls.
All right, India, all the way from India. Congratulations, guys.
Thank you. Thank you for coming.
All right, whoa. We're going a bit fast here.
Sorry.
India. All right, next team is...
You don't know, yes, you don't know. Say you don't know.
Yeah, EPFL, Switzerland.
First captain. Congratulations.
All right, after that, we have the UK.
We just stand right there. Congratulations. Good. Okay.
Yes, your team.
Yes.
Yeah. Incidentally, this is also Anastasia's team.
And Mary's team.
Yeah, why you didn't?
And Mary's team.
Where's Andrew? Andrew left. Okay.
All right. Up next, I think it's Croatia. Yeah, Croatia.
Diploma. You also have many goals. It's good.
All right, next up is, Denmark. Congratulations, Denmark.
So who is team captain?
I am.
You are, very good.
Whatever.
How?
Next team is Greece. Bravo.
So now we need genuine excuse and we'll sign it later, okay? You will forgive us. Oh, it's a big party. No, I did something wrong. No.
Okay. Next team is a special team that we all love. It's Ukraine. Thanks for coming, guys.
You're not team captain, you're not team captain, you're not team captain, you're team captain. Yes, I had similar earrings yesterday. Okay.
All right, we're approaching top 10 territory, and we have a team from far away. It's Colombia.
Akash, to speak on memes. On memes. Akash, you speak on memes. Here we go. So, who is team captain? Very good. Congratulations. This is your diploma. I'll sign it later. Okay.
With the prices, I think they're also semifinalists and finalists, right?
Yes.
Yeah. All right, so now we had 21 teams this year, which means that the next 10 teams are officially in the top half. And at number 10, we have Sweden.
No.
Canada.
Wait, I need to pass diploma. Who is the team captain? Yes, diploma, it's very important.
Nice. Paid our photographer.
So if you think I know which slide is next, I don't know which slide is next. So let's hope on the good. Yes!
Congrats, ETH!
So who is team captain?
Thomas.
Thomas, okay. He's busy. Thomas, congratulations. That's yours. Let's move this way.
I think we need to move a bit to the left now. right.
Have to return back, right?
Yeah, I guess.
Yes. No, not Sweden.
Sweden, congrats.
So the Oki is the fastest. Okay, who is the team captain? Not you. Oh, the one with the flag. Very good. Sorry. Oh, you very.
All right. Oh.
So this is a place where we just need to consciously take a pause, because it's a borderline between people who didn't make the semifinal to people who made the semifinal. And it's a natural pause to walk you through some our calls and suggestions. So the first one is that we have a solution database. It's a place where you can store the reports based on your solutions or your presentations. It's stored on the platform which is called Zenodo. It's a repository for research articles and other data and research outcomes. And through that, you'll get the DOI number for any your submissions there. And this way, your research in form of presentation or report is citable and can put in your publication list when you need to use it for some applications or to enrollment to master or so. So for using this very nice opportunity, you can either send us the presentations or we'll have a special channel on Discord to upload your presentations there. And we'll take care of storing it and providing you with information. That was the one. Something more advanced what we have in IPT is actually in-house journal, which is called Emerging Scientists. And it's been founded exactly for the purpose of letting IPT participants to write research articles about their IPT solutions and have this experience of publishing process. So when you pass the peer review, you read the reviewer's comments, you address the reviewer's comments, you see the I mean, but you still try to be polite, all this sort of stuff. And it is a great place where you can actually practice that, not going to some fancy and spooky adult journals. This is a journal which was designed for pedagogical purposes, and it is a great place to start with this publishing experience. There's a fancy link. You see, I'm not super good in making QR codes, but I think you'll manage. And also, IPT conference proceedings. So yesterday, we had very interesting and special event which lasted with beer, but it was still very nice, and we also had online presenters. For them, it's a great opportunity to be in the IPT, but not be in the IPT, but still experiencing, in some sense, these IPT solutions. So, as a part of our Zenodo platform, we also publish proceedings from this conference. So all the abstracts which were submitted for the talks yesterday gonna end up there. And you can see the abstracts from the proceedings from last year, which we released just before the IPT week started here. And with that, we can move on the next slide and also continue about the conference proceeding. And Arnaud wanted to give a couple of words to you as a feedback about how the conference went yesterday and what is his reflection about it. And he has slides, apparently.
Hello, guys. Okay. It works? Oh, perfect. Hello. I'm Arnaud. I'm the former LOC president for last year. I think Mathieu did a very good job, not as well as last year, but that was kind of good. That was kind of good. Congratulations, that was fantastic. Thank you. Unfortunately, I couldn't make it for the selective fights. I was kind of very sad not to see the first fights, but I saw the IPT conference and was very happy to see a lot of problems, a lot of very nice solutions. So I wanted to speak 30 seconds about what I've seen in the G3 room. I think it was G3. G4. G4. Yeah. Okay, the room in which I was. It's kind of good. So I pick and choose some things. I've seen anti-bubbles from Team Denmark, from Mali. was very nice. I really liked the surface anti-bubbles, the original interpretation of the problem, nice presentation, furry experiment, and good vibes. It was very nice. A word for Victor from the Polish team for the bright spot. It was a very nice presentation, nice retrieval of the phase method. I felt kind of bad for him because he just passed after as the bright spot was presented, and he felt very disillusioned by the fact that he's a second to present the same thing, but it was a very, very important work. It was very nice, so that was a great job. Congratulations. The Ukrainian team with Anna on the unrolling tape, qualitative presentation, very nice slides, nice results. Presentation quite a little quick, but a lot of parameters were investigated, clear conclusion. Congratulations. And then I arrived on two very, very nice presentations. I couldn't say which one was the best. One was fast, clear, nice presentation. There were polished slides, very, very nice presentation, comparison of experimental and theory and stuff like that. And another one, the slides were not so much polished, but very good vibes, very good presentation, experimental and theory were explained. It was very nice to hear about that. So we had Luka from Croatia and Darina from Ukraine. Congratulations to you two. You gain the special prize, anti-bubbles.
So it seems like it's already spoiled, but I want to give some honorable mentions because in G5 room, there were so many high-quality presentations that were really high level, and it was wonderful to see all of them. I want to give some specific mentions. The Greek team had an amazing bright spot. Begrudgingly, I can say that the Swedish team had not only one, but two amazing presentations on both the Golden Board and the Bright Spot. Also, I was very fond of Canada's alcohol soundcheck. But the winner in the end, as it was a bit spoiled, is Lucas Heck from Brazil that did it from online.
IPT president, you get to give the diplomas? Yes.
I gave the diplomas to you.
No, not to me, to the people.
To you guys. So, yeah, please, Darina, Luca, and we don't have Lucas because he's online. Please join me here. Before we fit the entire team. Congratulations.
Congrats.
Lucas!
Maybe we'll ship you the chocolate if there's some budget left.
We can pass it with Brazilian team, can we?
Oh, yeah.
Mateus, can we pass the chocolate with Brazilian team? To Lucas. What? We'll brief you later. Okay. So this was another round of applauses which we gave for the IPT conference people. And it's another piece of I'll be asking you for favor about, that we tried last year, didn't quite work. But we're really keen to make very cute and fancy reels and shorts for people who love physics, so they start loving IPT2 as much as we do. And as long as you are, during the preparing your experiments or during the preparing your presentations, are often filming something very nice and well staged, it is exactly what we ask you to contribute to us, so we can edit it and use on Reels. If you need a credit, we of course put it in the video description. We'll have a special channel for that on Discord, and we really love you to have your contributions, because it's so many lovely and visually cute physics which happen in the IPT problems, and it's a great shame that not so many people can enjoy watching it. So let's change that. So please stay tuned to the Discord on the announcement for the call for those videos. And another thing which we are very much advertising around is the submission form for the problems. So the IPT problems are not decided somewhere behind the curtain. They are decided by the community. And this two-stage process, which is supervised by Alberto because he is IPT president. Okay. Yeah, because he is IPT secretary. And we are collecting your suggestions for problems for the IPT, for the next IPT edition, and we collect them all together, we have a committee to review them, and then we send them for the vote which are supervised by the IOC in each country. So IOC in your country, national representatives, collect your suggestions about which problems you prioritize, which problem you find not interesting you don't prioritize. And for the first stage of this selection process, please provide us suggestions for the IPT problems for next year. It's a Google form, it's on the website, and it has a deadline. Sadly, people are missing those deadlines, but because it's a selection process two-stagey, we have to be ready roughly early summer with a long list for the problems. Did everyone scan it? Raise your hands who scanned it. Okay, it's going to be very few contributions. Please scan it and add it to your bookmarks, okay? Great. And we invite people to executive committee. So the team which I showed you before, which is run by me as the IPT president, the executive committee who are responsible for international businesses of IPT. And it is a great community of people who love physics itself and love making physics experience for students great, smooth, and exciting. And if you feel like someone who wants to help us to make it even more enriching, please also contact us. We'll have a Discord channel for that too. Yay! So now we move to the next stage.
This is actually the stage where if we had put a betting system in place, you would have gotten like all your money. I want to make specify something. For the prizes, I was a bit confused whether we kept the chocolate for the semi-finalists or everyone, but I'm sure the semi-finalists and the finalists won't mind to share. So the teams that didn't get a big triangle of chocolate, please get it in the end, okay? Because we forgot to give it to you. You deserve it.
So we display the points on the slide, and before it was points earned in the selective fights, and now it's going to be points earned in selective fights and in the semi-final, because it's what determines whether the team makes to the final or not. And we start with one of them.
All right, Brazil.
Hello. This is for you. We're gonna sign it later. We're late. Congratulations, Team Brazil.
All right, get ready now, because the next team is the United States.
So it's a very famous team which has 3 Nathans.
Guys, amazing job. I get you too.
Oh wait, already got. Hi, Royston. You should go in the middle, and then we are like on the edges. Okay, where is correct Nathan?
Yes, one of them, yes. Yes, this guy.
Congratulations.
Thank you.
Congratulations, team.
So now we're entering top 5 territory. So these teams are dangerously good. And the one we have right now is actually the second team of Poland. Is that right?
Yes.
Warsaw, thanks for coming, guys.
Which is a That's a party. Okay, who is the team captain? Kuba. Hi, Kuba. Congratulations. Why you have 2 badges? Sorry. Well done. Is the last diploma in my hand.
Yes.
Have another pack there, don't worry.
All right. So in 4th place, we've got Team IPT.
I also don't remember who is team captain. Tak, we have the following break bit, and for this break, I think I need Christus. No? Okay. No, you're also a good person. Oh, I need you, both of you. Can you come to me, please? Yes. So I feel the next part which we're going to discuss, it's Christus as a person who just built the spirit of IPT meme part, should give reward for. So my plan is that Akash gonna speak and Chris is gonna pass to shake hands.
Yeah, okay. So this was definitely not done in the lunch and like the last 10 minutes. But I decided to sort of recap a little bit of the memes in 4 slides. So there's not a lot of them there. There were some really great ones. We all saw them. So first of all, thank you, all of you, for taking part in it. And so, yeah, quite a few good ones here, right? I did not write down who made them, but I guess you all know. These are all before today. So whoever made them, thank you very much for making them. I suppose this was supposed to be the bell of the ETH. So let's just take a moment for the memes. And then we went to the fight today. Some really good stuff. So yeah, that's some really good stuff. I'm hoping for some of this after this. So whoever made that, yeah. I'm sorry I couldn't add everything. It didn't have so much time, but there were some really good stuff. And thank you for holding down the fort. Both the teams of Italy and Germany this year were in the final, so must not have been easy when we were gone. But thank you very much for making the memes in our absence. And I want to, before we give the best memes, I want to kind of give a shout out to team leads as well, who seem to participate in this thing. Can you? And two, yeah, what I like about this thing is that you made that yourself, didn't you? Where are you? Yeah, great job. And also, this was made by Benoit, team lead from Team Germany. He's not here. He was watching the YouTube stream and was like, don't worry, I'm just gonna meme the entire time. And a final mention before that. Yeah, to our precious secretary, who was supposed to be doing secretary stuff. Thank you for setting the bar high. And also thank you very much to Maya. I know this is a lot of plagiarism going on there. He just takes your memes, posts them there. We have a problem with it, we'll talk about it. Okay, so then we come to the awards for the two best memes of... Okay, so we were supposed to have one, I guess. So is this a chocolate bar? You guys have to share. Oh yeah, I had not seen this one before somehow. But while we give the chocolates, could the two people who made them come here? Do we have a chocolate? Okay, you guys have to share, but that's fine. Please give a big... Can we play this? Can we play that? It's a video. Oh, you... So, you can shake hands with and take a picture with the cat man. Okay. I mean, it's a video, but I guess it's not playing. But I really like that. Whoever, you guys, that was an amazing video. If you haven't seen that, go back and see it. It encapsulates everything. Have you seen that? This is great. Okay. So thank you, everyone. And I guess we have to move on. Do you want to say something to motivate the people?
I'm going to try. I don't have any voice left. So, as you probably saw in the sneak peek slide, anxiety is raising because do you want to know the host of the IPT for 2025? A cap out. No? You don't? Yeah? I may already know the answer. The host for the IPT for 2025 is... Yeah. Poland. Thank you, Christoph. I hope you're all excited. I hope you all come to Poland the next year. It's going to be amazing. I mean, look at the level of the memes by Polish team. We're gonna see the bobber in real life. And now, I will give it to our president.
No.
No?
Good.
Oh, this?
So this is a very important slide. And this is a moment maybe to chill everything down and to reiterate again that it's not only memes which unites us, but it's also love to physics. And those guys who were doing the final fight today for us did absolutely extremely great job, both in preparing their solutions, in putting things together, in writing everything down, and they demonstrated to us a great excellence of physics fights, and we all enjoyed it today. Did we enjoy it today?
All right, so we're finally getting to it, the moment we've all been anxiously waiting for. We're going to start with the team that's in third place, okay? I want you to build up the hype. All right, so on third place of the IPT 2024, we have...
So we have a big bag of goodies.
Yes, so you guys don't only win the chocolate. We've got some special goodie for you. You all get a pair of ETH socks, so you get to remember the place.
You, okay, hand. Congratulations.
Thank you. All right, so I guess that leaves us with two teams. And I have to say, having seen the grand finals, it was super close, and I think any team could make it and would certainly deserve it. But it is the rules. We have to crown a winner. So I want you guys to make even more noise to hype up who's going to win the IPT 2024. All right, so the team that won the IPT 2024 is Germany!
Well done. Okay. No way.
We can hug later. Is this the one?
So we have another bag of goodies.
All right, so you guys get the extra goodie. Not only can you keep warm in winter with the socks, you also each get a Swiss pocket knife with ETH. And I'm sure you're going to get it to smuggle across the border, so I think it's
Wow.
Feels good, right? So now we're going to invite France, who got second place. Congratulations, guys. Also get
So I failed, yes?
Congratulations. All right, so I have a question. How ambitious are we? Should we try to get everybody on stage again a picture? Is that even feasible?
Yes.
Yes?
Yes.
Let's all squeeze together. Let's all hug together. Make a last memory. So I invite you all on stage to come and try to make a picture, okay? Please stay close. Do you think it works?
Thank you. I think they had to applaud you.
Excuse me. We can leave the slide with the Polish auditorium.
Yes.
It should be nice because the next.
Yeah. Let's do that.
What?
Let's
Well, if you have in front of me, I've been scrolling a long time.
It's in the end.
It is not obvious that it's about IPT at all.
Okay, yeah, maybe.
Okay.
Guys, push to the back. We need to make a lot of space for everyone.
Cool. Oh, guys, we actually must squeeze, so it's going to be very COVID-friendly. Otherwise, it's our ambition not going to work. Thanks a lot for giving the talk. Sorry? Thanks a lot for the talk. Had to sign stuff.
Yeah, I think it was a terrible idea. Yeah. All right, guys, I have another idea.
Can you make him?
Guys, let's make 2 pictures, okay? Otherwise, we're not going to survive.
Okay.
Okay. All right. So could we have? Okay, guys. So it was a bad idea. We're gonna take the picture when you sit, actually. So thanks for coming on stage.
Good try.
Yikes. Terrible.
Ah, we have IPT there. Oh, that's not bad.
Oh putain. Putain, je cuis. Genre j'ai les couches et tout là. Putain, c'est trop cool que l'Allemagne ait gagné. Quand j'ai vu, je l'ai signé le certificat, j'étais là genre. Congrats.
Congrats. I didn't say you thank you. No, but you said me thank you, and I didn't say you thank you. But you know that I'm appreciating everything. Of course. You do.
I just wanted to make sure everybody knew about you, though. By the way, I realize I didn't get to sign all of these certificates. So teams, please check your certificates, and if it does not have my signature, I'll give you an autograph for free. All right, so how can we do that?
Can you ask them to sit in the middle part?
Ah.
Maybe on stairs, because I can't.
Guys, people on this side, can you go closer to the middle and sit in the middle and on the stairs so we can all be in the...
Still gonna go and make
Yeah, we're trying to make it. I'll sign it for you.
Yeah, I need it.
Yes, there's a nice photo of it.
After the photo.
Yeah, of course. Did you guys also get your extra shot?
Yeah, for the team.
The team, you have it?
We have the blue one and the yellow one. It's a perfect combination.
The blue one's my favorite.
Everyone stands in the rows. If you've got the same, the crowd shoulder to shoulder better.
Yeah. So this, you mean, sorry. Sit down.
Sit down, yeah.
I think teams in the middle, it's easier if you sit down. And try to squeeze. Oh yeah. Can we have some people in the first row too? Yeah, all the LOC people, Execom people, helpers, please come in front.